أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم فقال ربكم ادعوني أستجب لكم آمين يا رب العالمين الحمد لله رب العالمين الرحمن الرحيم مالك يوم الدين إياك نعبد وإياك نستعين اهدنا الصراط المستقيم صراط الذين أنعمت عليهم غير المغضوب عليهم ولا الضالين آمين اللهم اجمع شمل المسلمين والكريستيان والأمة في مدينة دباو وسلم دائما مجتمعنا هذا بالسلم والأمن والتقدم في بلدنا هذا آمين يا رب العالمين ربنا لا تزغ قلوبنا بعد إذ هديتنا وهب لنا من لدنك رحمة إنك أنت الوهاب إنك أنت الوهاب ربنا وفي الآخرة حسنة وقنا عذاب النار وصلى الله على خير خلقه سيدنا محمد وعلى آله وصحبه وسلم سبحان ربك رب العزة عما يصفون وسلام على المرسلين والحمد لله رب العالمين آمين يا رب العالمين.
In the name of the Father, Son, and Holy Spirit. Amen. Our most gracious Heavenly Father, we come to you today to praise and worship you and give you thanks for all the things you continue to provide for ourselves and our families. Father, we humbly ask for forgiveness for all the times we have offended you. When we forget to acknowledge your presence in the image of our brothers and sisters, and for moments we fail to be good stewards of the blessings you have given us. Continue to guide and protect each one of us, Lord, that we may always walk in the light of your everlasting love and mercy. Grant us, Father, with your comfort in times of distress and with your strength in times of weakness. Bestow upon us your unending grace and healing, that we may in turn become instruments of gentleness and compassion to others. We ask all this in the name of your Son, our Lord Jesus Christ, with the prayer and the intercession of our Blessed Mother. Amen.
Manama, mawantog ka. Warag po ko ilingkoy ko. O Diyos, kahibulong ka.
Yeah. Bye. That is happy presentation.
Ang simbahon ko. Busa ikaw lang ang alagaran ko.
Mga kababayan, ang pambansang awit ng Pilipinas. Kayang magiliw, kaya sa silanganan, alam ng puso, sa titik mo'y bumay. Lupang hinirang, kuya ka ng magiting, sa manlulupin, di ka pasisigil, sa nagtatapulog sa simoy at sa langit ng pagaw, ay hinatang tulang awit sa pagkayang minamahal. Ang isang ng matawad mo'y tagumpay
Okay, to formally begin the webinar, so we are pleased to have Engineer Olga Joy L. Hirasta, our IECEP Iligan Bay Chapter Governor, to deliver the opening remarks. Ma'am?
Good noon, everyone. Thank you to each and every one of you for being here with us today. We are very pleased to be able to welcome those of you that have been with us for a long time now, as well as those who are new to the group. Today's marks our second week seminar on microelectronics trend, and we are proud to be able to host it today through online webinar. Before we get started, I would like to express my sincere appreciation to all of you who generously help us make this event come together to become a successful, especially the speakers who will share their knowledge with us. We could have done it without you. In today's gathering, we have 3 speakers from industry and academe. You have all been chosen to be a part of this event due to a mutual passion to increase technical presence and equip universities in the field of microelectronics technology. We need you as much as you need us, and that's why we are grateful to have you join us here at this seminar. Thank you very much for listening. I ensure that seminar will be profitable and fruitful for everyone present here. Have a good day.
All right, so thank you, Ma'am Olga, for that wonderful remarks. Okay, so now without further ado, we will turn the time over to our first presenter. So our presenter today received his bachelor degree in Electronics and Communications Engineering as cum laude from University of Science and Technology of Southern Philippines, or USTP, formerly known as Mindanao University of Science and Technology, or MUST. He also has a master's degree in Electrical Engineering, major in Microelectronics, obtained from Mindanao State University, Iligan Institute of Technology, or MSU IIT. He joined Analog Devices Incorporated in 2014 and currently holds the key role as a senior analog IC design engineer. He has been involved in a non-professional patent application about designing edge combiners with symmetrical operation range at high speed. His interests, experiences, and research capabilities includes design of DC-DC controllers, low dropout regulators, bandgap preferences, and other ADI product enhancement. Now help me welcome our first presenter, Engineer John Michael Gorospe, and he will be presenting the topic Cap-less LDO for modern system on chip design. Sir JM.
Hello, good afternoon, everyone. So is my voice clear?
Yes.
Okay, so good afternoon again, everyone. I am JM Gorospe. So I work in Analog Devices Incorporated as an IC design engineer. So today I will share to you this topic. So a capacitorless LDO for modern system on chip design. So I will discuss later what is a capacitorless LDO. So moving forward, so let me set the expectation first. So this talk is a crash course on low dropout regulators. Since most of the participants have little knowledge on microelectronics, so I will discuss the basics on LDO. How does it work? What is an LDO? How does it function? And then the second part is that I will discuss about the stability, the PSRR, and the load transient of an LDO. So why these three? There are many specifications of an LDO. So I will focus on these three alone because these three specifications will be greatly affected if we will remove the capacitor in the output of an LDO. And let me apologize. So I will not, I think I will have no time to discuss the last part. So initially I prepared this talk for a 2-hour talk. So I think I will be limited in time if I will discuss the last part. And I think there are many information I can share to you without discussing the last part. But if you are interested really in the techniques to improve the load transient of a capacitorless LDO, so you can always ask me at the end of my presentation. Okay, so now let's begin. So this is the outline of my presentation. So I will be, there will be an introduction, then I will discuss more on LDO, and lastly, I will discuss specifically on a capacitorless LDO. Now for the introduction, let me start first for the motivation. So the question is, why do we need to design a capacitorless LDO? Is it not a conventional LDO enough? So a conventional LDO is an LDO that has an...
Excuse me, Sir Jay. Can you please share your screen if you are already... Yeah, the participants can see it, cannot see it. Okay, thank you so much.
Thank you for the reminder. The host is disabled participant screen sharing.
Okay, so we will fix it for a while.
Yeah, sorry.
Okay,
For the meantime, so let me just discuss to you that, yeah, the conventional LDO, so it is an LDO that has an external capacitor. So external meaning the chip is outside, the capacitor is outside the chip. That's why it's an external capacitor. So now I can say
okay,
my
I
screen.
think it's, yes. All right. Thank you so much, Sir JM.
Can you see it now?
Yes, we can see it now.
So again, so this is the outline of my presentation. So let's begin with the introduction first. So in the introduction, I will discuss the motivation. So what is the motivation of designing a capacitorless LDO? Since an LDO with an external capacitor is already existing, so why do we need this kind of LDO? So as technology becomes more and more advanced, technological problems also become more complex. So these complex problems requires complex solution. So that is why system-on-chip design was introduced. So a system-on-chip solution incorporates numerous functions in a single chip. So for example, the latest technology right now is the M1 chip produced by Apple. So it is present on their MacBook and on their other product. So this is the best example of a system on chip. So in a system on chip, it is a single chip that incorporates many functions. For M1 chip, it is the CPU, the GPU, the memory, and other blocks. So that's what a system on chip looks like. It incorporates numerous functions in a single chip. So, diba, in previous product, the CPU is in a separate chip, the GPU is in a separate chip, or a memory is in a separate chip. But in this system on chip, more functions were integrated in a single chip. Then how does it relate to my topic about LDO? So the more complex your chip becomes, the more complex also the power management system becomes. And in the power management is the fundamental blocks of all electronic systems. Why? Because no matter how good your design in your CPU or in your other blocks, if there is no power, so basically the chip will not function well. So that's why power management is an integral part of every electronic system. Again, where does the LDO will come in? So the LDO is a part of your power management. So the under power management is the load dropout regulator. And again, so why we need a capacitorless LDO? So the more the complex the system is, the more LDO you're going to need, because different blocks requires different voltages. They require different current sources. Now, imagine if, for this example, just imagine if you have 6 LDOs you designed for this specific application. And imagine if that 6 LDOs requires 6 external capacitors. So you have 6 external capacitors. So if you will produce this chip, if you will produce 1 million of this chip, so you will need 6 million of that external capacitors. So that's a lot. So if there's a way to remove that capacitor, so we will save a lot of area and we will save a lot of cost. That's where the capacitorless LDO comes in. So imagine for that 6 LDOs, 4 of them, you can design them to be a capacitorless LDO. So you already saved 4 external capacitors. And if there are 1 million of these chips, you are saving 4 million of that external capacitor. So that is the motivation behind designing a capacitorless LDO. Now, so that's all for the motivation. So let's jump on the function. So I always talk about LDO, but what is really an LDO? So an LDO is a load dropout regulator. So it's a type of linear regulator. Linear meaning there are no switching activity inside this block. So it's purely linear, controlled by a single loop or multi-loop. So, and the other variant of a regulator is the switching regulator. So switching regulator is a dynamic kind of a regulator. It has switch inside of it. So a low dropout regulator is a linear regulator. So it is called low dropout because you can see here the basic block diagram of an LDO. So an LDO has an input supply, which we call the Vin. It has also a reference voltage, Vref, and a ground, and it has also a single output, which is a Vout. And in that output, you will connect your load devices. So an example of load is it can be an ADC, a DEC, an oscillator, or any digital blocks. So you will connect that load at the output of your LDO. And in this block diagram, I just model the output load as a variable resistor. Now, again, it is low dropout because basically an LDO, the supply voltage and the Vout voltage are almost equal. Not equal, but they have more or less 100 millivolts gap between the two if you will subtract the two. That's why it's called low dropout. And the lower the dropout, the higher the efficiency of an LDO become, but the more challenging the design will become. So again, this is an LDO. This is the black box of an LDO. So an LDO provides a constant output voltage. So that's an LDO. It provides a constant output voltage regardless if the supply voltage changes. So example, you have a battery here. It's your supply. It's supplying the LDO. Now that battery changes through time, right? It is not constant. But no, even if that Vin voltage or that supply voltage decreases with time, the LDO should provide a constant voltage, even at varying input voltage. And then the LDO provides a constant output voltage even if the temperature changes. So inside your chip, the temperature is not constant, so it will vary and depending on the application. So for example, the temperature on the chip varies from -40 to 125 degrees Celsius. So the output of the LDO must maintain a constant voltage regardless if the temperature varies. So what is the relationship between temperature and LDO? Now your LDO is composed of many transistors, PMOSFETs or BJTs, and that transistor has a transconductance. or GM. So that transconductance varies a lot with temperature. It either increases or decreases depending on the temperature. And if that transconductance varies with temperature, your Vout also will vary if you will design the LDO poorly. So in short, no matter if there is a variation in the temperature, your LDO must remain a constant, must maintain a constant output voltage. Now, not only temperature, but also you have a load here. And the load that you connected to the LDO, the current consumption of that load also varies. For example, it varies from 0 to 100 milliamps. For some LDOs, like high power LDO, it varies from 0 to 2 amperes or 1 ampere. So even if the load current varies, the LDO should maintain a constant voltage at the output. And not only the load current, and also the process and the mismatch changes. So no two chips are created equal. So the process changes. Process meaning there are temperature that performs faster. There are transistor that perform slower depending on the process. But even though, no matter what process you are in, your LDO should maintain a constant voltage regardless of the process, regardless of the wafer. So that's it. So that's the basic definition of an LDO. In short, if you will forget everything, just remember in your mind right now that an LDO will supply a constant voltage regardless of any changes in your system. So, okay. So let me move on to the other part of my presentation, which is the function. Now we know what an LDO is, but before designing an LDO in a transistor level, it is much better to know how it is much better to know its it is better to know it is beneficial if we will model it first. So we will start at the very basic, and then we after we model the LDO, we will implement it in a circuit level, in transistor level. So the next step is to create a model of an LDO based on its functions. Now we know that an LDO will supply a constant voltage. That is what we know right now. So this is the model. So this is the model of an LDO. I just use a variable resistor. So you have an input voltage, you have a variable resistor here, and you have an output pin, Vout, and you also have a load that is connected at your output. So a certain load will be demanded to the LDO. So this load current will flow from Vin through this variable resistor and out to your Vout. And we learned from previous slide that an LDO must maintain a constant voltage even if Vin changes and even if the load current changes. So for example, let's take this model. And what is your Vout? So you can get your Vout by simple KVL, right? So your Vout is just equal to your Vin, or your supply voltage, minus the drop in the variable resistor, which is IL times R. IL means the load current. This is the load current needed by your blocks that is being supplied by the LDO. So this is the basic equation of an LDO based on this model. Now, if Vin increases, for example, your Vin increases from 2 volts to 3 volts real quick, so it increases. What will happen to your Vout? So based on this simple equation, your Vout will, you're right, it will increase because Vin increases. Now, remember the concept of an LDO. LDO should maintain a constant voltage. Now, what should we do based on this model? What should we do in order to compensate the increase in the Vout? So what we can do based on the equation is that we need to increase the resistor, correct? If we increase the resistor proportionally, we are increasing this term. Thereby, we are countering the increase of your Vin. So if we can counter this increase in Vin, we can maintain a constant Vout. So that's the key. So meaning, in simple term, you just need to adjust the resistor in order to compensate any changes in your Vin. And not only VN, but I said earlier that your load current also changes. Now, what will happen if your load current suddenly increases? So for example, the block that is connected in your LDO wakes up, it transition from hibernate mode to high power mode. So suddenly it requires a large amount of current. So the current increases. Now what will happen to the V out of your LDO? So based on this equation, the V out of your LDO will decrease, correct? Because this term, the negative term, will increase. Now intuitively in this equation, what we need to do is we will just reduce the resistor value. If we can reduce the resistor value, we can compensate the increase of the load current. But if we can compensate the increase of the load current, therefore, we can maintain a constant output voltage, even if the current increases or decreases. So that is the concept of this model. So in short, we can just model an LDO with a variable resistor. So that's the very basic concept on LDO. But you might ask me a question, so how can we control this R? So this R is a variable resistor in our model, but how can we control this how can we control this so that we can have a value of resistor that will counter the effect of the increase in your VIN or the increase in your load current? So that's the big question. Now, let me introduce to you the feedback concept. So this is a negative feedback loop. Negative because we have a negative sign here. So I will explain here as basic as possible how can we control this R. So in order to control the resistor, we need some feedback mechanism, which is what shown in the diagram. This feedback, so the purpose of this feedback is it will going to sense your V out. So it will sense your V out, or in other words, it will monitor the value of your V out. Then the monitored value will then be feedback to your input. It will be feedback to the input. And in the input, you have a reference voltage. So this is the purpose of the reference voltage. The purpose of the reference voltage is that so that you will have a known voltage value. And so this known voltage value will then be compared to your feedback voltage. Now you have two quantities. You are comparing Vref and the VFB. This VFB is the sensed voltage in your V out. So you're going to compare it. If there is an error, so you have a V error here, and that error will be amplified by your amplifier, and then it will change the voltage of this node in order to adjust the output resistor. And now we have another piece of information. Not only do we need a variable resistor, but we need our variable resistor that changes with voltage. So if we change the voltage here, we are changing the value of the resistor. And through this feedback, we can now change, or we can now control the value of the resistor. So let me expound a little bit about this feedback. Now, so let me introduce to you case one. So just for example, you have an output voltage of 1.8 volts. Okay, you have an LDO and you design it to have 1.8 volts output. Now, going through the loop, so the feedback will sense this 1.8 volts. And if you have a feedback factor of 0.5, for example, you have a gain of 0.5 in your loop, in this feedback path, the output that you will going to expect in this node will be 1.8 times 0.5, which is 0.9. And this 0.9 sensed voltage, you will compare it to your reference voltage, which is, in this case, I designed it to be 0.9. Now, you are going to compare these two inputs. And if these two inputs are equal, then you will not have an error voltage in this node. So if you do not have an error voltage, then you will not, the voltage at this node will be constant. It will not increase or decrease because you don't have an error. So meaning you will maintain the value of this resistor. So that's what you want, right? Because there's no changes in V out, so you don't need to change R because there's no changes in your V out. Now, how about if the voltage suddenly decreases? For example, the voltage decreases to 1.7 volts, and we know that we don't want this to happen because we are designing an LDO. An LDO delivers a constant voltage. But what if there's a case where the output voltage suddenly decreases? So it decreases to 1.7 volts. So what will happen? So what will happen to the loop is that it will sense the 1.7 volts, it will multiply it again by 0.5. So you will now have a 0.85 voltage at this node. And this 0.85, you will compare it to 0.9 volts reference. So basically, you're just subtracting the two. And the difference of that one is 0.05 volts. This is what you call the error voltage. And this error voltage will then be fed to your amplifier, then it will be multiplied. And so that since it's positive, then the voltage at this node will increase. Now, if the voltage of this node will increase, what will happen to our resistor? It will decrease. Why will it decrease? Going back to our equation, if Vin increases, if Vout decreases, so we need something, we need to change this equation so that we can counter the effect of the drop of the Vout. So what can we do is we can reduce this R. Because if we can reduce the value of this R proportionally to the value of the decrease of this output voltage, we can somehow counter the effect of the decrease of that output voltage. We can counter that one by decreasing the value of your R, thereby maintaining a constant voltage. So basically what I'm trying to convey here is that I'm trying to explain how this loop reacts if there is changes in the output voltage. So this is how the loop reacts. So in summary, if you don't have an error voltage, meaning if your reference voltage is equal to your sense voltage, then we're good, we're happy, meaning we attain the perfect output voltage. But if ever there is an error or there is a difference between the two quantity, meaning we need to adjust the value of R by increasing or decreasing this voltage node. So that's the basic explanation of this feedback network. So I will not discuss anymore the case 3 where the Vout suddenly increases because it is just the same concept as the previous cases. So yeah, it's just the same. Okay, so now I will move on to the next part of my presentation, which is the circuit. Now we already modeled the LDO. So this is the basic model of an LDO that we can get. So we already created a model out of the function of an LDO. We know that an LDO delivers a constant output voltage. And based on that concept, we already derived a model out from that concept. So and this is the model. So how can we implement this in a circuit level? So we can implement it this way. So let me introduce to you the basic parts of an basic LDO. So this is what you call the feedback network or the feedback part of the LDO, the K. K is its gain. And in this circuit, this is the resistor feedback. So we can implement this feedback circuit by just simple resistor. So take note that the purpose of this feedback is to sense the voltage. And we can do that by just putting a resistor. We can sense this output voltage by putting a resistor here. And this resistor will feed back a portion of this output depending on the ratio of your R1 and R2. So it will be feedback to your amplifier. So that's the purpose of your feedback part of the circuit. Now, how can we implement this in the circuit level, this combiner and this amplifier? Actually, we can just implement this one with a single transistor amplifier like this one. So going back to our basic electronics, an amplifier, the function of an amplifier is that it compares the two input voltage, and based on the difference of that input voltage, it will amplify or it will increase it will magnify the difference of the input voltage, and it will feed that different amplified voltage at the gate of your pass device. So we can just implement this one by using a basic amplifier. You can implement it using a simple amplifier, folded cascode, or whatever. And now, our variable resistor, how can we implement this variable resistor? Now, this variable resistor can be implemented by just using a transistor. So in LDO, or in low dropout regulator, we call this PMOSFET as a pass device. Why pass device? Because it allows the passage of current from your supply to your output. That's why it's called a pass device. And this is a PMOSFET, but there are other architectures of LDO that uses an NMOS FET. But in this talk, I will just show you the PMOS architecture. So now, this is now your LDO. It's very basic. So you have a feedback block, you have an amplifier, and now you have a pass device or a PMOSFET that serves as a variable resistor. So this is now your basic LDO. So next, sorry. So we are now done with the introduction part. So let's discuss more about an LDO. So the question is, how does LDO work? So given this circuit implementation of an LDO, how does this work again? I already showed you earlier how does this work, right? So, but maybe you are asking this question. How come this PMOSFET act as a variable resistor? How does this act as a variable resistor? So in order to answer that, let's look at its small signal model. So this is the small signal model of this PMOSFET. So don't worry about the small signal model. So in this part of the presentation, just assume that it is. So just agree with me that this is the small signal model. So my point why I show you the small signal model is that to show you that a PMOSFET has an output resistance or output impedance that is, and we can call that output impedance as an RDS, or the drain to source resistance. So this is the key to our discussion about LDO. So this, if we can change this value, then if we can control this value, then we can control the VR through the feedback loop. Okay, so through this small signal model and disregarding the loop, we will just disconnect this loop first. We can derive the V out. So V out is just the GM times, or the transconductance times the VGS, or the gate to source voltage of this PMOS device, times the RDS, or the output impedance of the PMOS FET. So this is the basic equation that we can get. And so my point is this equation. We know earlier that in order to create an LDO, we need to have a variable resistor, correct? Because we need to vary the resistor depending on the value of your V out. And also we want this resistor to change inversely proportional to the voltage. For example, if the VGS decreases, we want our resistor to increase, and vice versa. If the VGS increases, we want this resistor to decrease, which is true based on this equation. So therefore, we can really model that variable resistor by just implementing it with a simple PMOS device, or an NMOS in other architecture. So that is the same concept. And again, so this is the equation of the LDO without factoring the feedback network. So without factoring this feedback network, we can get the V out by just having a KVL of the output, which is the V out will equal to the supply voltage minus the load current times the RDS, the resistance we can see at the output of the PMOS FET. So this is the basic equation we can get. Okay, So now we now know how an LDO works. So let's move on to the second part of my presentation, which is about I will be discussing now the stability, the PSRR, and the load transient. These are the specification or the parameters that you will encounter when you design an LDO. Again, why do I focus with these three characteristics of an LDO or specification of an LDO? Because I will be discussing the capacitorless LDO. And the capacitorless, so the stability, the PSRR, and the load transient will be greatly affected if we will remove that external cap. And that's why I need to discuss these three specifications. So let's go to the stability. So if we are designing an LDO, so we cannot avoid discussing stability, because if your LDO is unstable, then you have a crappy LDO. So that we don't want that kind of LDO if it is unstable. And if we are discussing stability, we will encounter this term, closed loop gain. So what is this closed loop gain? So closed loop gain is the gain from your Vin or from your Vref to the output of the LDO. So that's your closed loop gain. It's the gain from your Vref to the output of the LDO when the feedback is closed, when you have a feedback network. Example, this one. Since you have a feedback, then your closed loop gain is just the transfer function from your Vref to Vout. So you can derive that one if you have a basic knowledge of feedback network. So we can derive that one, we can derive the closed loop gain, and we can arrive at this equation. So the AO part here is the open loop gain. So this is the total gain of your error amplifier plus the gain of your pass device over 1 plus K AO. Your K is just your feedback factor. So that's your K. In my previous example earlier, the K is 0.5. So that's the K, your feedback factor. And based on this equation, if the open loop gain or the AO is much greater, so if your K times AO is much greater than 1, you can simplify this equation by just 1 over K, meaning 1 over the feedback factor. And if you substitute all the values here, the R1, the R2, the closed loop gain or your Vout over Vref is equal or approximately equal to 1 plus R1 over R2. So now, for example, you want to set your Vout. Let's say I want a Vout voltage of 2 volts. So how can you set the output voltage of the LDO? So you can set the output voltage of the LDO by deriving the closed loop gain, which for this example, it is just equal to 1 plus R1 over R2. Now you might think, for some of you, this equation is common, right? You already encounter this equation in your basic electronics. So this equation is just the equation of a non-inverting amplifier. So basically an LDO, in a simplest term, it is just a non-inverting amplifier. But the difference is that this amplifier is able to provide a large amount of current to your load. Now, you have another gain, which is the open loop gain. So what's the difference between the open loop and the closed loop gain? So the open loop gain is the gain also, it is the gain from your Vref to Vout, the same as the closed loop gain. But the main difference is you will derive the transfer function from Vref to Vout by disconnecting this loop. For example, imagine you cut this loop open. So the VFB, this loop is not anymore connected to this node. So it's open. So that's your open loop gain. It's the gain from the Vref to Vout without this feedback loop. And there is another gain, which is the loop gain. So what is the loop gain? The loop gain is the gain around the loop. It's the gain around the loop. So if you will go around this loop, and you will get the transfer function, then you will get this loop gain. Remember, loop gain is not the gain from the Vref to Vout. It is not that kind of gain. Loop gain is just the gain around the loop. And so if we there's a technique to get this loop gain. So, and I will not discuss that anymore in this presentation, but if ever you will get the loop gain, so this is the equation of the loop gain. Just this closed loop gain, open loop gain, these are the general equations. So the loop gain basically is just the open loop gain, AO, times the feedback factor, like the feedback factor K. So why am I showing you this? Because this is important when we will talk about stability of an LDO. Because out of these equations, for example, the closed loop gain, we can now derive the stability criteria of an LDO. So in order to know if our LDO is stable or not, then we need a criteria in order to verify if the LDO is stable or not. So the criteria is this one, the K times AO, or your loop gain, your gain around the loop should be less than or equal to -1. So what does this mean? So in simplest term, the -1 means a 180 degrees phase shift. So example, your sine wave becomes, forget about that. So for example, it only means that if you have a negative value, meaning you have a 180 degrees phase shift around the loop, and you don't want that one, because if you have 180 degrees phase shift around the loop, meaning your LDO is unstable. Now, how can we apply it in a real design? For example, you design an LDO. This is the very basic LDO. You get the loop gain. So you get the transfer function, you compute it, and you arrive at this equation. So the key here is that you will know that you are stable or not by just purely doing the math. Because if K times AO will be equal to -1 or negative some value, meaning there's something wrong in your equation, or there's something wrong with your LDO, because an LDO should be a negative feedback. So having a negative here will make the LDO a positive feedback. So you don't want that again, because if you have a positive feedback around the loop, your LDO will become an oscillator, and you don't want an oscillator in an LDO. So that's a very bad LDO design. Now, I discussed to you the mathematics, or the stability criteria in terms of math, that it is that your LDO will become unstable if you have a less than or equal to -1 loop gain. Now, how can we appreciate it intuitively? So let's analyze this LDO intuitively without equations. So what if your Vout has this phase? It increases like this way. So again, remember, an LDO should not have this one, because your LDO should provide a constant output voltage, right? So if there is a shift here, your VFB will sense this Vout. So you will have this one. So the phase of this waveform is the same as the Vout, because you are just having a resistor here, so it's the same. There should be no phase difference between the two, and this signal will travel around your error amplifier. And if ever after it travels around the error amplifier, and you also did not get any phase shift, and that's good, that's what we want. We don't want this to shift, the phase of this one to shift. And if you have this output, if you have this voltage waveform here, now it is in the input of your pass device, or it is the input of your PMOSFET. If you're looking at this PMOSFET, this is a common source, right? The source is common, and the input is in your gate and the output is in your drain. So this is a common source amplifier. And if you have this kind of waveform here, remember that a common source amplifier introduces a 180 degrees phase shift. So what do you expect at the output? You expect at the output is a 180 degrees phase reversal. So in your input, in your output, you started with this one, increasing voltage. But going around the loop, you now have this inverted output. And you want your LDO to behave this way because you can cancel that increase in the V out. Now imagine if again you have this phase, your LDO increases, and then you sense that voltage, you have the same phase. And remember, your error amplifier has many capacitors in it. And that capacitor will introduce phase shift. So for example, in worst case scenario, this is your sense voltage, and going around the error amplifier introduces a 180 degrees phase shift. And remember, in our stability criteria, if this loop introduces a negative 180 degrees or a 180 degrees phase shift, then we are in trouble because the LDO is now unstable. Because what will happen? For example, there is a phase reversal in this node. Now, you still have another stage, a common source stage. And again, a common source stage will introduce another 180 degrees phase shift. So all in all, the output, now the output coming from the feedback is the same phase as your original output. Then what will happen if you add these two? What will happen is that your output will increase more. Instead of decreasing, it will increase and increase and increase until it will rail to your V-in. So we don't want that kind of LDO. So what causes this phase shift around the loop? So if you depending on the value of the phase shift, your LDO will be stable or unstable. Now, what causes this phase shift? Reactive components causes phase shift like inductors and capacitors. But mostly in LDO, we are dealing more on the capacitor, except for inductor if we have an external capacitor. Now, a single capacitor causes a 0 to 90 degrees phase shift. So if there are more than one capacitor inside your amplifier, or there are many stages in your amplifier, so it will causes a phase shift of more than 180 degrees. And we don't want that to happen. Otherwise, our LDO will become unstable. So this phase shift causes the system to become unstable. So we already defined the stability criteria of the system. Now, so if I'm an analog designer, if I want to design an LDO, I want to know what causes my LDO, what are the causes why my LDO becomes unstable. And I mentioned earlier that reactive components will introduce phase shift, and that causes instability of your LDO. And in order to stabilize an LDO, a good design engineer must know how to get the poles and the zeros of your LDO. And in order to get the poles and the zeros of your LDO, you need to get the transfer function from your VREF to your Vout. And in order for you to get the transfer function, it is a must that you know how to model this in a small signal. It is a must that you know how to convert this LDO into a small signal model, which is this one. And again, I will not discuss here how I derive the small signal model of the LDO, but my point here is that in order for you to stabilize the LDO, it is very efficient if you know the location of your poles and your zeros. And to know the location of your poles and zeros, you need to get the transfer function from your VREF to your Vout. And I will not discuss anymore how I derive these equations. But basically, if you can derive the closed loop gain or the loop gain of the LDO, you will now then you can now get the poles and the zeros of the LDO, and you can also get the DC gain of the LDO. Now, this location of the poles and the zeros is essential, is very important if you want to stabilize the LDO. So in this case, I have two poles. The P1 or the pole 1 is located in the V out, and the pole 2 is located at the output of your error amplifier. The placement of this pole is essential if you are going to stabilize your LDO. And again, you need to derive the equations, even if it is not accurate enough, but at least you have the ballpark values to where these poles are located. That's very important. Because, for example, you design an LDO and then you did not derive the equation, you did not derive where the poles and the zeros are, then what you're going to do is you will just apply trial and error. So you just simulate the circuit, see the stability. If it's not stable, you're going to adjust the LDO. And again, you have no idea where to adjust because you don't have an idea where is the location of your poles and the zeros. Okay, so that's my point. You need to derive this equation. Now, in order to proceed, these are the equations that we derived from the previous slide. Now, we will now plot this equation in a Bode plot. So what is a Bode plot? A Bode plot basically is a logarithmic plot where the x-axis is the frequency and the y-axis is the DC gain and the other y-axis is the phase. Now, the question is, why do we need to plot it in a Bode plot? The reason is to know the frequency response of your LDO. If you want to know how your LDO behaves across frequency, then you need this kind of plot. In the Bode plot, we will see the gain and the phase of our LDO across a frequency range. So the gain and the phase is what we need in order to evaluate if the LDO is stable or not, based on the stability criteria. So let's remember that our goal is to have one pole inside our unity gain frequency. So again, why one pole? In this equation, we have two poles. But if you want your LDO to be stable, you need to have a single pole as much as possible inside your unity gain frequency. Why? Because one pole causes 90 degrees phase shift. So if you have one pole, you are sure that you will not have a 180 degrees phase shift because you only have one pole. Now, if you have two poles, then there's a danger that your LDO will become unstable because you now have two poles. Then two poles meaning your feedback loop can introduce a 100 degrees phase shift. Now, let's plot this quickly. So in the low frequency, your gain is constant. That's your DC gain because it's in the low frequency. So it is constant because you don't have any poles and zero yet in low frequency. Now, what will happen if you encounter a pole? For example, in this frequency, you encountered a pole. What will happen to the magnitude of your LDO, the output, the gain? What will happen is that it will decrease 20 dB per decade. So that's the property of a single pole. It will decrease 20 dB per decade. And then again, if you encounter another pole, it will decrease again 20 dB per decade. So all in all, if you have two poles, it will decrease 40 dB per decade. So this is how your gain behaves across frequency. Now, how about the phase? If you don't have poles and zero yet, for example, at low frequency, there's no phase shift, meaning your phase is zero around the loop. Now, what will happen if you encounter a pole? Right? You encounter a pole. So again, remember that a single pole introduces 90 degrees phase shift. So what will happen is that it will introduce 90 degrees phase shift. So that is your pole. So, okay. So again, it will just stabilize to 90 degrees if you don't have any poles in the system. If you encounter another pole, it will introduce again another 90 degrees phase shift. So all in all, if you have two poles, it will introduce 180 degrees phase shift. Now the question is this LDO stable or not? Now, we can answer that question if we can identify two terms. And the first term is the phase margin. So the first margin is one indication that your LDO is stable. So what does phase margin mean? Phase margin is just the amount of margin needed for your LDO to become unstable. So for example, how do we get the phase margin? So we can get the phase margin at the 0 dB gain, meaning at the unity gain, this one. This is your UGF, this is your unity gain, where the gain is 0 dB. So if you project that to your phase, then in the x-axis, that is your phase margin value. That's 90 degrees. So phase margin is just equal to the negative 90 degrees plus 180 degrees. So in this case, your phase margin is 90 degrees. So it is quite stable because remember, in our stability criteria, your LDO will become stable if you have 180 degrees phase shift. Now, in this plot here, the phase margin is 90 degrees. So what does it mean? It means that the LDO needs a 90 degrees phase shift for your LDO to become unstable. So meaning the bigger the value of your phase margin, the better. Because meaning it needs greater amount of phase shift for your LDO to become unstable. So that's what it means. Now, it is not enough to define the stability of the LDO by just getting the phase margin. The other criteria based on our stability criterion is the gain margin. So what is the gain margin? Now, the gain margin is it is the measurement from your, so it is when, for example, your phase becomes 180 degrees, like this point here, it becomes 180 degrees. So your gain margin is the difference between the 0 dB, so 0 dB minus the gain at this point where your phase is negative 180. So for example, the gain here is negative 10 dB. So negative, so 0 minus 10 dB, so your gain margin is 10 dB. So that's the amount of gain needed for your LDO to become unstable. So remember, you might ask, okay, so in our body plot, actually we reach 180 degrees. But that is not the phase margin of your LDO. The phase margin of your LDO is at unity gain, which is 90. Now, so at 180 degrees, we don't care anymore in this graph because we don't have gain, right? Our gain is less than 0. So we don't care anymore whether our phase shift reaches 180 because we don't have gain. In short, our LDO will not function around this frequency. So it's okay. Now, to finish the stability discussion, let me show you another case where the LDO is unstable. So remember that we have two poles in that architecture, pole 1 and pole 2. And how can I relate this into capacitorless LDO? So how can I relate it in a capacitorless LDO? So I'm just repeating myself. So in the equation, you can notice here that pole 1 has CL, or the load capacitance. So in your conventional LDO, this CL has a very big value. For example, 1 microfarad, 2 microfarad, or others, it can reach to 10 microfarad depending on the application. And that's very big. So what does it mean? So it means that this pole will move into a very low frequency, like this example. It will move into a very low frequency because you have a very large capacitor here. Now, what will happen if you will design a capacitorless LDO? Basically, you're going to remove this CL. So you don't have a 1 microfarad of capacitor. Instead, you will only have a picofarad capacitor. That's very small. Now, what is its implication on stability if you have a very small external capacitor? So what will happen is that the pole here at the low frequency will move into high frequency, just like this image here. You will notice that pole 1 moves closer to pole 2. And we don't want that to happen in an LDO. Remember, if you have 2 poles inside your UGF, meaning there's a tendency that you can introduce a 180 degrees phase shift, which we don't want. For example, in this point here, around this frequency, you don't have any phase shift because you don't have a pole. But suddenly you encounter a single pole. So your phase drastically degrades to -90. And again, you encounter another pole. And it will decrease drastically to 180 degrees. So looking at the unity gain at 0 dB, your phase margin is now 180. So -180 plus 180. So actually you don't have margin anymore. That's why your phase margin is 0 because you are already unstable. And you also notice in this one that your gain margin, remember the definition of the gain margin is you will get the moment you reach -180 phase shift, you will measure the gain. So in this case, you have a positive gain. So meaning 0 dB minus, let's say, positive 10 dB, you now have a positive 10 dB gain margin. So that is unstable. So in industry, usually the customer requires at least 45 degrees phase margin across process, voltage, temperature, Monte Carlo variation, at least 45 degrees, including parasitics, layout, effects. And the gain margin, usually, they will demand at least 10 dB, -10 dB, at least 10 dB of gain margin. So I hope you learned something in terms of the stability of an LDO. Again, my point that I want to convey is that if you want to design an LDO, a good designer should know how to derive the poles and the zeros equation so that you can stabilize the LDO efficiently. Because if you derive the equations, then you know where are those poles and the zeros, and you know exactly what to change in your circuit. So the second part is the PSRR. So don't worry, we now have 2 more topics need to be discussed. So PSRR, what is PSRR? PSRR is a power supply rejection ratio. So in simplest term, again, PSRR is the measure of how good your LDO can reject noise or can reject ripples. So for example, you have noises in your V-in or in your supply. So for example, in your application, your V-in or your supply voltage is a switching regulator. So we know that switching regulator is a noisy regulator. It has a ripple like this one. Now, you need an LDO. So the purpose of your LDO is to reject as much as possible the noises that appear in your supply. So you need to minimize it as much as possible. Now, how can you measure it? How can you know that your LDO is good enough or not good enough? So that's your PSRR, the power supply rejection ratio. So mathematically, it is just a ratio between your output and the input. So since you want a very low noise at the V out and given a noise at the V in, so meaning usually the value of your PSRR is negative, since this term approaches zero. So 20 log approaching zero is negative value. And the key here is that the more negative your PSRR, meaning the more it is capable of rejecting noise from your input to supply. Now, maybe what I can share to you is that how can I improve the PSRR of the LDO? Now, before I can answer that question, the first question you need to ask is that what are the paths here that contributes to the noise in the output? Meaning, you will need to identify the paths that is possible that the noise can couple from your supply to your Vout. So in this particular architecture, there are three paths. Path one, your noise here can couple to your Vout via your Vref to your amplifier, then out to your Vout. Then the next path here is from your supply voltage, then to your air amplifier, then to the Vout. Then the last path is from your supply to the Vout. So there are three paths. And you need, again, a good designer must know how to derive the transfer function from your Vin to Vout. So because before instability or in getting the output voltage, we derive the transfer function from your Vref to Vout. And this time, when we analyze PSRR, we need to derive the transfer function from the supply voltage or your Vin or where your noise sources are to your Vout. And that's very important to get. Because again, for example, okay, I want to improve the PSRR of this LDO. By just looking the schematic and without doing the equation, then you might get lost. So what are the parts here that I need to improve? Should I increase the gain? Should I increase the size of the pass device? Or should I adjust the stability compensation? Or should I improve the Vref? So there are lots of things you need to consider in order to improve the supply rejection of an LDO. And again, a good designer knows how to get that equation. It may not be that accurate, but again, as long as you can get the ballpark values, then you're good enough. Because from that ballpark values, you can now adjust your design. Rather than you don't have an idea, so you're just, again, trial and error. Simulate, and hoping, praying to God that the PSRR will be okay. And I think that's not a good idea. You need to analyze it carefully because God has already given us the ability, the mind to do it and the skills to do it. So let's continue the PSRR. So again, in this presentation, I will not anymore show you the derivation of the equations, but I will show you the final output of the PSRR. So time check, it's 2 p.m. before 2 o'clock. And again, so for example, so as an IC design engineer, it's important that you know how to explain the results. Because you must know why your output behave that way. So you cannot just simulate it and let the simulator do its thing, and then if the PSRR is good, then you report it that, okay, I got the good PSRR. But if someone will ask you, oh, why is the PSR waveform looks like that, then you need to be able to answer that kind of questions. So now let me show you, or let me explain to you the waveform of a PSRR. So I said earlier that the PSRR depends with frequency. That's why when we are plotting PSRR, it is with respect to frequency and in a logarithmic axis. So at low frequency, your PSRR usually is very high. It's in very negative value. The question is, what determines this value? For example, you have an application that, okay, I want a very high PSRR at DC, meaning at low frequency. Now, how can you improve that one? So looking at the equation, you can improve it by increasing the PSRR of your amplifier and increasing the PSRR of your VRF. So that's why equations are helpful, because now you know what to change. If you're only concerned with DC, now you're going to change is the amplifier and the VRF. You're not going to change the output stage because you're only concerned with the DC value. Now, what will happen if your frequency increases? Now, what happens is that again, so this is path 1 and 2. The major contribution of your path 1 and 2, of this part of your PSRR, is your path 1 and 2. Now, what if your frequency increases? Your PSRR degrades. It degrades. It becomes worse. The question is why? Why does it become worse? It becomes worse because you can see here that in path 3, you have this equation. And the bigger your gain of your amplifier, the better your PSRR is. Bigger gain means better PSRR. Now, what happens as you increase your frequency? We already see it in the stability, that when we increase the frequency and we encounter a pole, the gain suddenly reduces, right? It decreases 20 dB per decade. So if your gain decreases, your PSRR will also degrade, like this one. It will degrade. And when it will degrade, it will degrade in this frequency, or it will degrade in a higher frequency. It all depends on the bandwidth of your amplifier. And then at high frequency, usually at a high frequency, what dominates your LDO is the output, the path 3, this path 3. So if you can see here, path 1 and 2 has no contribution to the high frequency PSRR. It's 0. It has no contribution at all. So the path 3 has a contribution to the high frequency. You can see here that it is just a parallel combination of your output impedance and the impedance of your capacitor. That's why in your simulation, you notice that if you have an ideal capacitor, and if you have a very big capacitor here, your PSRR will improve. Why? Because the characteristic of a capacitor, if we recall that it acts as a short at higher frequency. So at high frequency, this capacitor acts short. Ideally, if you don't have a parasitic resistor and inductor, it acts as a short. If it acts as a short, you can think of it this way. You have a noise at your Vout. So your Vout varies because of noise. It goes up and down. Then this noise will be seen at the Vout through this path 3, right? It will be seen here. But since you have an ideal cap and you are in a high frequency, this noise will not stay here. It will be decoupled to the ground. So the noise will be decoupled to ground. That's why your PSRR improves drastically if you have an ideal capacitor and if you have a very big capacitor. So that is also the reason why if you want to design a capacitorless LDO and your system or the blocks that you need to supply requires a very high PSRR, it requires a very high PSRR at a high frequency, and it requires a very low noise supply, then capacitorless LDO is not for that design, because if you remove this external cap, your PSRR starts to degrade like this one. So if you have a capacitor that is not ideal, what will happen is it will not go down. What will happen is it will be limited by the value of your parasitic resistor and parasitic inductor that you can see in your capacitor. So that's why if you want to have a very good PSRR, you need an external capacitor on an off-chip capacitor that has a very small parasitic R and very small parasitic inductor. And that capacitor usually is very expensive. Okay, and I think I will not discuss this anymore. So this is just the summary on how you can improve the PSRR of the LDO, which I already discussed. Okay, finally, last but not the least, I will now discuss the load transient. So what is load transient? So load transient is an event where the load current suddenly increases. So in this event, we still want our LDO to maintain constant values. So usually that happens. For example, this is your load, and this load, let's say this is an ADC, for example. Then your ADC is in hibernate mode. So in hibernate mode, you only consume a very little amount of current. So your LDO here has a very small amount of current. It will provide very small amount of current. And you have this V out. So your V out is constant. Now, suddenly your system wakes the ADC, or the ADC suddenly wakes up. So it is in high power mode. So what happens is that it will consume a very large amount of current, let's say I max. Now, what will happen to your LDO if the load current suddenly increases? Will the V out increase or decrease? It will decrease. Again, we can analyze this intuitively by just using a very simple equation that the V out is just equal to your V in minus the load current times the resistor of your pass device. So if your IL started to increase, then this term will decrease, right? So therefore your LDO decreases. That's why if you design an LDO and you test the load transient, you will notice a dip here or a delta V here that goes from this, that looks like this. It will, your LDO will have a dip. So this we will also call this an undershoot. So again, I already explained earlier that this loop will respond to that changes so that it will correct this dip, so that your LDO now becomes constant. Momentarily, there is a dip, but your LDO, the loop of your LDO will take care of the changes, then it will maintain a constant value. Because again, that's the definition of your LDO. And what if again, your ADC now is in a hibernate mode? So from high power to low power. So suddenly, your I load decreases. So what will happen in your V out if your load decreases? So if your load decreases, your LDO will suddenly increases. That's why you will see a spike here, a positive spike. That's because your load suddenly changes. And again, your loop will take care of that changes. It will manage to correct this spike to a certain level and will make your LDO to have an output, to have a constant output. So that's how a load transient that's how your LDO behaves if you have a load transient. Now, what is its relation in a capacitorless LDO design? So let us derive the equation of this spike here. So we can derive the equation of these spikes by using this equation, that this delta V out or the spike here is dependent on the amount of change of your current. If there is a bigger change of your input current, let's say from 0 to 0.1 amp, you will have this amount of undershoot or overshoot. But if your load current changes from 0 to 1 ampere, for example, then this will increase. The spike here will increase because your delta V out is dependent on that increase of current. Not only in current, but also your delta V out is dependent on your delta T. What is this delta T? Your delta T is inversely proportional to your bandwidth and to your slew rate. Now, bandwidth is that the bigger the bandwidth, meaning the faster your LDO is. So the faster your LDO, meaning the faster it can react to the changes in your output. Because remember, ideally, your LDO should react very fast if there is changes in your VOut. But again, there are capacitors, there are poles in your system. Poles can make your system become slower. That's why if you have many poles, then you can have a slow LDO. So if you can, so your delta T, you want your delta T to be very small so that your delta V out will be very small because your LDO can correct it as soon as possible. And you can make this delta T smaller by making your bandwidth bigger or making your slew rate bigger. So your slew rate is just how fast you can charge and discharge this node. So that's a slew rate, the rate of change of the voltage or current in this node with respect to time. So the bigger the slew rate, the faster your LDO can react. And now there's another quantity that can affect this load transient. And that quantity is the CL or the load capacitance. So this is now I can relate the capacitorless in the CL because if you have an external capacitor, then that's good because having a big capacitor, let's say 1 microfarad capacitor, can greatly help these transients. It can greatly reduce the transient. But if you have a capacitorless LDO because you need a capacitorless LDO because you cannot afford to have an external capacitor, then your V out will, the spike here will really degrades. It will increase. This will go down much smaller and this will go up much higher if you don't have an external capacitor. So that's a disadvantage if you will remove the capacitor in an LDO. Now, why is it important? Why not just leave it as it is? Because as we can see, if we will allow enough time, the LDO will just become stable, right? It will just maintain an output voltage. But why do we need to correct this, or why do we need to make this in a reasonable value? It is because, for example, there is an event in your chip, and then your LDO starts to decrease abruptly because there's something happening inside the chip that the load current increased suddenly. And if it increases suddenly and this becomes very, very small until zero, for example, it reaches zero and then it goes back, there is a possibility that if in that chip you have a voltage monitoring system and that voltage monitoring system detects this spike, then the chip might restart, or the chip might restart unnecessarily. And you don't want that chip to restart. For example, in the automotive, and that chip plays an important part in the safety on that automotive. And you don't want that to restart anytime. And it suddenly restart because there is a trouble in your LDO. So the driver might have an accident in a worst case scenario. So you don't want that. That's why you want to control this value. And how about in the high side? You don't want this also to increase very high because remember, your LDO is supplying another block like an ADC, a digital, an oscillator. Now, that block might not be able to withstand a very high voltage spike. So you might damage those blocks. That's why you need to manage this spike. So that's why my next topic should be how can we address these spikes in a capacitorless LDO, knowing that in a capacitorless LDO, we don't have an external cap that will help us minimize these spikes. But again, for the interest of time, so time check, it's already 2:13 p.m. So I think I cannot discuss anymore this part here, the adaptive biasing and the transient boosting technique. But again, in any case, if you want to know more about this, I think what I can do is to send these slides to the organizer, and if you want a copy of this slide, you can freely get it. So for free, because there are no confidential information in these slides anyway. But let me finish my talk in this one, since I'm discussing a capacitorless LDO. So let me end with this. So what is the advantage of having an external capacitor if you are designing an LDO? So based on this talk, this external capacitor will help stability if you want your pole, dominant pole, at the output of your LDO. So it will help the external capacitor because you are just separating your poles. You are having in an enough distance between the two so that your phase shift will not reach 180 degrees. And the next advantage is it improves PSRR at high frequency. So we see it in our discussion in the PSRR that if only you have an ideal cup, or if you have a cup that has a very small parasitic inductance and resistance, then you can have a very good PSRR at high frequency if you have a very large capacitor. And again, lastly, in terms of load transient, it will greatly reduce the delta V out because your delta V out is inversely proportional to your external capacitor. Now, obviously, the advantage of the cap LDO will become a disadvantage of your capacitorless LDO. But the key here is that you only need to design a capacitorless LDO if and only if you don't need high PSRR and you don't need a very small delta V out. So you can manage to design your LDO without a capacitor. Now, what is the advantage of removing that capacitor? First is less hardware cost. As I mentioned before, if you have an external capacitor and if you have 4 LDOs with an external capacitor, you have 4 external capacitor. And if you have 1 million of this kind of chip, then you have 4 million capacitors. So less hardware cost. Then if you remove capacitor, meaning you are saving a PCB area. Diba? In today's technology, the smaller the PCB area, the better, because you can make your technology, for example, your laptop, your cell phone, to become much smaller because you have a very small area, PCB area. Then the next one is less pin out. Remember that, so this is the capped LDO. So you have an LDO inside and you have an external capacitor located at your PCB. And in order for your LDO in order for this external cap to be connected inside your chip, you need a pin. So you need a pin. And in system on chip application, you want smaller pin as possible, smaller number of pin as possible, because usually the number of pin dictates the size of your chip. So the smaller your pin, the smaller your size can become. So if you will remove an external capacitor, you can save a pin. So possibly you can save a chip area for that matter. Not necessarily, but you can. And so in your capacitorless LDO, you have an LDO, but your capacitor is inside your chip. It is inside because it usually ranges by of around, let's say 100 picofarad or 10 picofarad or 5 picofarad. So it's very small that you can design it inside your chip. Whereas your external capacitor, it's around 1 microfarad. So you cannot put it inside your chip. It's very big. Maybe 1 microfarad will consume most of your area in your chip, and we don't want that one. So I guess that's the end of my presentation. I'm very sorry I cannot discuss anymore the adaptive biasing technique and the transient boosting technique. But if you will going to ask this in our Q&A, yeah, feel free to ask. I can maybe give you a small hint about this technique. So I guess that's all. So any questions?
Okay, so thank you so much, Engineer John Michael Gorospe, for that very comprehensive and interesting topic about low dropout regulators, or LDO. Okay, so now we will be entertaining some questions from our participants. By the way, our participants is coming from different parts of the Philippines. So we have here Negros Occidental, Manila, Batangas, Cebu, Cavite, Pampanga. So not just Northern Mindanao, but we have also participants coming from Cebu, no? Cebu, and then Laguna and Eastern Visayas. Okay, so to start with our first question, we have here from MQ, Edson Rosete. The question is, The question is, what is the best region of operation for the fast transistor, linear or saturated? Or is it more of a matter of what application the LDO is used in?
Okay, thank you for that question. So let me answer first the first question. So what is the best operation condition of the fast transistor? So ideally, we want that fast transistor to be operated in the saturation region, because if you notice in saturation region, you have a much constant output impedance, and you don't want that output impedance to change much. Why? So first, in the perspective, for example, of your PSRR, you want a very high PSRR LDO. So you don't want that resistance to change from this value to that value, because any change of that resistance will be converted to a change in the Vout voltage, and Vout voltage means noise. So you don't want that. So as much as possible, you need to size it in a saturation region. But the question is, do you really need that one? Somewhat your second question is correct. Do we need it? This is so can we size it in a linear region? Actually, we can allow that LDO, especially at low load, we can size it in a sub-threshold part. So we can do that one. But again, take note that there are some parameters of your LDO that will be affected. Actually, sometimes the stability also will be affected because your Rout will change. But because you need to, as a design engineer, you need to weigh things. If I will size it this bigger for this PSRR, you need to graph it. You need to assess it. Is this much area needed for this PSRR? Or if I increase this fast transistor in order for me to size it in saturation region, is the benefit of having this kind of area has an impact or not? Because there is a diminishing return if you will size your fast device bigger. I guess that's my point. So it really matters in your application. Can you handle that sub-threshold region? Is it okay for your application? I guess that's it.
Okay, so thank you so much, Sir JM. So it's a matter of weighing the pros and cons. Okay, so our next question is from Peter Ong. Mr. Peter Ong, the question is, can we improve the stability of capless SoC when we put large capacitors than what is needed? Again, can we improve the stability of capless SoC or system on chip ICs when we put large capacitors than what is needed?
Yeah. So actually, I don't get the last part, but let me answer how can we improve the stability of the Cap-less LDO, knowing that the poles will become much closer to each other, thereby introducing a negative 180 degrees phase shift. Now, usually in a capacitorless LDO, your dominant pole, you don't need to put it in the output of your LDO. You can put it inside your LDO. So you can do that by using a Miller compensation. I think some of you are familiar with that Miller compensation. But actually, in our team, we discourage using Miller compensation because it will degrade the PSRR, because you will have a feed forward path from your input to output. So that degrades PSRR. But you can do that if you want, if you don't care about PSRR, so you can do that. And also you can introduce zero. So a pole introduces a decrease of 90 degrees phase. It will introduce a decrease of 90 degrees. A zero will increase the phase to 90 degrees. So if you can cancel that pole that causes instability by a zero, you can do that one, so that you can cancel that pole and you can make your LDO stable. But by putting a large capacitor, so yeah, in order to design a good LDO, you must put a capacitor that is only needed by your design. So don't put too much, because too much capacitor equates to too much area. Remember, big capacitor equates to a bigger area. So you need to compute those values in order to optimize your design. Now, I only need this value of capacitor to make it stable, then do that one. So I think that's all.
Okay, so thank you, Sir JM. So our next question is coming from Mr. Chris Kevin Adrivan. The question is, what is the primary consideration in choosing the pass device? Again, the
Okay.
question is, what is the primary consideration in choosing the pass device?
Yeah. Again, there are many things to consider if you're going to size the pass device. Maybe I cannot mention all, but first I can mention that the size of your pass device depends on your load current. So your load current will range, example, from 0 to, let's say, 1 ampere. But for capacitorless LDO, it will not go beyond 1 ampere. So maybe it's 10 milliamps, 100 milliamps, it's possible. So that's the first one. You need to optimize that size based on your load current. So you need to size that one. And then second, again, if you have a PSRR constraint, then you need to size it based on your PSRR requirement. Or because you need to have enough GM or enough transconductance of that last stage. So because if you have too much transconductance, too much gain, for example, and you don't need that too much gain, based on the PSRR equation and based on what architecture you're going to use, it will affect the PSRR negatively. And so I think that's the two main point. And then what type of pass device, whether NMOS or PMOS. So depending, again, it depends on your architecture. So usually, in my experience, we use an NMOS if we want a high PSRR, because an NMOS is a good isolator. You can isolate the Vin, the supply, to the output if you have an NMOS. But the drawback is usually you need a high gate voltage. So maybe you cannot afford that one if you have a very low supply, or you need a charge pump to do it if you have an NMOS. And usually we use an NMOS pass device if we want a very small area. Because remember, NMOS is much more, you can size the pass device smaller if you have an NMOS compared to a PMOS. And also, NMOS inherently is much faster than a PMOS. So if you want to have a good load transient response, if you have a good load transient response, then if you can, then choose an NMOS device. So I guess that's it. Hope I did answer your question.
Okay, so thank you, Sir JM. By the way, we cannot see your face. So the next question is from Samantha Pandes. Mom Samantha asks, what are the instances or applications that PSRR and delta V out load transient response improvement won't matter?
That's a very good question, because if it will always matter, so we don't need to design a capacitorless LDO, right? So in my experience, again, in the industry, we need a capacitorless LDO if we don't need a high PSRR and load transient response. So what are those specific example or loads? So for example, if you have a digital load, so digital loads require supply. It requires LDO, it requires current, so it requires an LDO. So digital load is inherently noisy because there are many switching happening in a digital load. So you don't need a high PSRR in digital load, like clock, oscillators, or whatever digital load. You don't need a high PSRR because inherently it's noisy. So you can just have an LDO with a not so good PSRR. And also, again, in digital loads, usually it is really used in digital load. So in digital load, you are expecting large transients. You're expecting, because the output voltage changes drastically up and down, up and down. And so now what you need to consider here of your capacitor-less LDO, so as long as you have that transient, as long as it will not hit the minimum, the voltage monitor, and as long as it will not damage the preceding blocks, then you can have a load, the delta V out, for example, 150 millivolts, then that's okay. Compared to if you have a cap, you can have a delta V out of 5 millivolts or less. So that's how big the difference is. So yeah, usually it's in the digital loads.
Okay, thank you for that, Sir JM. So our next question is coming from Sir Alvin L. mentioned. So were there existing applications that previously used CAP LDO, but was then replaced with capless LDO? Its advantages? If yes, can you name some of them?
Yes, there are. In my experience, again, so in the industry, yes, there are. So there are cases that it was designed first as a CAP LDO since we are concerned with the noise, but upon checking the system architecture level, so we don't need the CAP because we can live with a decent PSRR and good load transient, because there are techniques also how to improve that in a capacitorless LDO. So yes, we replaced it with the capacitorless LDO since we don't need that CAP LDO. Again, the key is the application. The key is in the system level requirements. So if we can remove that CAP, then much better. If we can't, then it's okay. We will live with it. So there are cases, and it depends on the system architecture level decision making.
Okay, so thank you, Sir JM. So next question is from Franco Margallo. Sir, the question is, big C out make LDO more stable. So in capless, what element does make the LDO stable?
Okay. So actually, when I discuss stability, it's not the whole story of the stability. It's just a small part, because having an external capacitor may or may not help you in your stability. For example, if your external capacitor is a crappy one or it's a cheap one, that the capacitor varies from, let's say, 0.5 microfarad to 2 microfarad. Actually, it's a challenge to stabilize that kind of capacitor because it's a very wide range and your pole moves up and down in the frequency with a wide movement. So what element can you use in order to stabilize the LDO? Actually, what element you can use? So it's basically element, it's just capacitor or resistor. Because again, capacitor will introduce a phase shift. And you can create a zero by just using a series of a capacitor and a resistor. And you can use that to cancel a pole. Or you can use a band limitation technique or narrow banding, where you can use a Miller cap. So Miller cap will be enough. So instead of putting your dominant pole at the output, now you will be putting your dominant pole inside your LDO. And there are also other architectures like the flip voltage follower, where you can put your dominant pole at the output, but that architecture is very fast, where the poles are located at a very high frequency, where you can afford to put your pole at the dominant frequency. So there are many things you need to consider: the architecture, how many caps, how many resistor, how many poles, how many zeros you need to create, depending on your system, depending on the number of poles, depending on your architecture. I guess that's it.
Okay, so I think that is all the question from the participants. But I have a question, last question for you, Sir JM. So this is related to the LDO that I've designed, I think 3 years from now. So the problem with the LDO that I designed is on the output waveform, I can see that there is an overshoot voltage at the startup of the waveform. So what is the probable cause of that overshoot voltage at the startup before the output voltage stabilized to its stable voltage, output voltage value?
Okay, so actually that concern is more on the inrush current. So usually that's the effect of your inrush current when you when you power up your LDO and there's no proper sequencing or there's no soft start, you just on it right away. So when you on your LDO, so the loop, remember the loop is not yet in its proper biasing condition. So the current from your supply will flow directly to the output through that bus device. And that large current will introduce a very large spike in the output. Remember, delta V out, you can just think of it as I times R. So large I means large drop. So that's why you are seeing that large increase in the V out at the start. So it's more on the inrush current. So, and it's another part of an LDO that you need to consider in designing.
Okay, so to wrap it up, so as a whole, during the design process for the LDO, what is the most challenging part that you can say? Pray to God before that kind of problem when it comes to designing LDO. What's the really most challenging part?
Yeah, we have a recent project last year. So I cannot say the customer name because it's really confidential. But actually the challenging part is that when you change the architecture, really. For example, in the design phase, you already have decided the architecture. Okay, this is the architecture that I'm going to use because there are lots of architecture in LDO. So there are lots of architecture you can choose from. So as a design engineer, you will validate, you will have an architecture review. You review this architecture, you present it to the customer. Okay, this is the best architecture available based on this application. Now, the challenging part is that when the application change or when there is something in your design that you did not consider. That's why the application that you chose, you start to design, it will, for some reason, it will not work anymore because you missed some key important in the architecture design that you did not consider. So that's a very challenging part last year, that the architecture changed because there's a miscommunication down the chain. And I have no choice but to change that architecture drastically. It's a very different architecture. And that's the first time ever I will going to design that architecture in a very complex project, a time-pressured project. So that's really because I have a very limited amount of time to analyze everything and hoping that it will work. And that customer particularly is a very strict customer. So it needs a very thorough validation of your design that it's really working and there's no hiccups or there's no problem. So I think that's it. So as a design engineer, again, the tip I can give to you is really pay attention to the architecture review. Make sure that you've considered everything and communicate it to the lead design or to the customer if that's really the specs that they want or they want to change it because it will affect your design time.
Okay, so I think we already covered all our questions. Thank you so much once again, Sir JM. So as a mark of appreciation, so we would like to award a certificate of appreciation to our first presenter. So I think you can see it now on your screen, no? So certificate of appreciation is given to Engineer John Michael Gorospe for having shared his knowledge and expertise on Cap-less LDO for modern system-on-chip design during the lecture series on Microelectronics Session 2 held at Zoom web conferencing on October 30, 2021, accreditation number IECE 2009-00F223, signed by our Governor of IECEP IBC, Olga Joy Rasta, and the Secretary Genevieve Gatar. Okay, so thank you so much again, Sir JM. And I know that the participants really learned a lot, no, from your very detailed, no, detailed presentation. So we can now proceed with the online quiz and evaluation for the topic presented by Sir JM. So participants kindly go to the link provided in the chat panel to access the online quiz and evaluation. So you are only given 15 minutes to answer it, and then we'll start with the next topic of this webinar. Okay, we will be sending you the link for a while. Okay, so again, this will serve as your attendance and basis for your CPD units, no? Okay, wait. All right, I think, let me know if you can already see the, okay, by the way, please give a virtual clap for Engineer John Michael Gorospe for that very wonderful given talk.
This is the Electronics and Communications Laboratory of MSU IIT. Inside are facilities and technologies that allowed us to design and develop communication systems for a wide range of applications. One of which is the system that uses wireless electromagnetic radar for groundwater detection. It is funded by DOSTP Shared. The project aims to first evaluate the ability of electromagnetic waves to detect underground water, estimate its depth and quantity. Second, map areas with possible sources of water.
This program allowed us to practice and apply digital signal processing and RF engineering. These are knowledge and capabilities we gladly shared with our established network of neighboring universities around Mindanao through various training modules and exercises. This activity could be a basis for each of these universities to further their research capabilities in the field of electronics and communications that will eventually yield into more meaningful integration of electronics communication courses. Researchers get to collaborate with industry players to take the research product to another level of commercialization. This mindset has to change. They should think of making their product visible in the market and reach the end user via commercialization. Hence, MSU IIT partners with construction firm in Davao City, Iligan Light and Power Incorporated, PhilMeco, and Department of Agriculture.
The outcome of the program is in support to the goals and endeavor of DOST, which is to develop new technology and strengthen the capabilities of universities to conduct innovative research in Mindanao. Thus, research environment can help universities create innovative research and hopefully become world leader in modern wireless communication, microwave, and smart antennas by addressing the needs of industry, government, and the scientific community. It is just only a matter of time that the Electronics and Communications Laboratory will largely contribute to the worldwide modernization. This is the Electronics and Communications Laboratory of MSU IIT. Inside are facilities and technologies that allowed us to design and develop communication systems for a wide range of applications. One of which is the system that uses wireless electromagnetic radar for groundwater detection. It is funded by DOSTP Shared. The project aims to first, evaluate the ability of electromagnetic waves to detect underground water, estimate its depth and quantity. Second, map areas with possible sources of water.
This program allowed us to practice and apply digital signal processing and RF engineering. These are knowledge and capabilities we gladly shared with our established network of neighboring universities around Mindanao through various training modules and exercises. This activity could be a basis for each of these universities to further their research capabilities in the field of electronics and communications that will eventually yield into more meaningful integration of electronics communication courses. Researchers get to collaborate with industry players to take the research product to another level of commercialization. This mindset has to change. They should think of making their product visible in the market and reach the end user via commercialization. Hence, MSU IIT partners with construction firm in Davao City, Iligan Light and Power Incorporated, PhilMeco, and Department of Agriculture.
The outcome of the program is in support to the goals and endeavor of DOST, which is to develop new technology and strengthen the capabilities of universities to conduct innovative research in Mindanao. Thus, research environment will help universities create innovative research and hopefully become world leader in modern wireless communication, microwave, and smart antennas by addressing the needs of industry, government, and the scientific community. It is just only a matter of time that the Electronics and Communications Laboratory will largely contribute to the worldwide modernization.
Driven to develop, innovate, and be the pioneers of research and development in integrated circuit design in southern Philippines, and to cultivate microelectronics IC design awareness in Mindanao, MSU IIT's Microelectronics Laboratory responded by designing an integrated circuit chip, a 3-year project funded by DOSTP Shared with over a budget of 31 million pesos. One of the many key features of this microcontroller is its ability to tap into the telecommunication devices, which can further improve management systems. With the use of this developed technology, phones, tablets, or even the computers of individuals who enter the premises can be prompted to preview the necessary aid in the event, for example, that there is a need for evacuation or rescue. Aside from that, through the use of a network of sensors, the microcontroller is capable of monitoring an entire environment and status of an establishment or given area in real time. Data on factors such as temperature, humidity, and even the presence of physical movement can be processed and utilized to automate, say for example, the switching of indoor light or even air conditioning temperature control in an area. With the microcontroller's self-sustaining mechanism, it would enable industries and sectors alike to monitor, record, and organize data directly from the microcontroller. This way, sites or facilities are monitored 24/7 without the need to send personnel directly to the location, making the whole process greatly accelerated and undemanding. Smart agriculture can find an effective use of this technology by providing their facilities a more advanced method of approach concerning crop and environment maintenance. With the extensive and promising potential of this highly reliable technology, the way smart buildings, smart agriculture, industries, management systems, and sectors alike will be able to operate and function to a higher and better degree, thus paving a way to a more enhanced and progressive performance in the workplace. Being the pioneer and a leading institution to establish a niche in microelectronics integrated circuit design in southern Philippines, MSU IIT's Microelectronics Laboratory is leveling up its endeavor by engaging a system-on-chip integrated circuit design development. Over the years, it has been promoting innovation and awareness in microelectronics IC design in Mindanao by offering courses and trainings that will enhance and provide advanced skills to aspiring IC design and layout engineers in the region. As a result, the Microelectronics Laboratory has been producing more highly skilled engineering graduates to answer to the increasing demand for professionals with strong background and skill set in IC design. The Microelectronics Laboratory has accepted the challenge of the ever-growing demand in IoT devices. It has dedicated its pool of talents and resources to develop its first contribution to the demand. The InLight chip, an energy harvesting chip that aims to extend the battery life of existing IoT devices. It is capable of extracting indoor light energy to recharge a nickel metal hydride battery used for wireless sensor networks applications. This two-year endeavor is supported and funded by USAID Stride, a program that has the goal to stimulate inclusive economic growth by boosting science and technology research. Building upon the success of the InLight chip, the Microelectronics Laboratory took a major leap towards designing a system-on-chip solution for wireless sensor network applications, which is made possible with its funding agency, the DOSTP SHIELD, the mandated Philippine Council in the implementation of strategies in the industry, energy, and emerging technology, research and development sectors. With its 3.5 years of implementation, the project started a modular approach in designing the system.
By the way, participants, for those who have already answered the questions without the modifications, no, regarding those questions na hindi masiselect yung yung supposedly checkbox. So we will be giving you another chance to again answer the question. I will be posting you the link. But this is also only for the first session. So later on for the, first presenter, later on for the next topics, you will only be given one opportunity to answer the questions. Just to be fair for those participants na hindi nila nakita yung modifications, no, regarding the format of the selection of the answers. Okay, so thank you so much.
The wireless sensor node is composed of 3 fully customized circuit boards. The top board houses the PV cell for the light energy harvester and the sensors used based on the desired application. The middle board includes the RF module, which is essential for wireless communication purposes. Lastly, the base is the main board, which highlights the IECEP chip, along with the necessary external components. Located inside the chip are the 3 main circuit blocks: the microcontroller unit, the energy harvester unit, and the power management unit. The overall system works starting with the energy harvester unit. The energy extracted from the PV cell passes through the energy harvester unit to produce a suitable voltage used for charging the power source, which is the Varta V450HR nickel metal hydride rechargeable battery. With the help of the EHU, longer battery life and extended device operation are made possible. Subsequently, the battery is used by the power management unit to generate usable voltage rails of different values through the boost and back boost converters. The boost converter supplies 2.5 volts to the sensors and the transceivers, whereas the back boost converter provides 1.2 volts to the MCU. Lastly, playing the biggest role is the microcontroller unit, which serves as the brain of the WSN. The microcontroller equipped with its peripherals, UART, SPI, and I2C, is used to interface with different sensors and establish communication with different nodes. The MCU can be programmed to fit the needs of the users in terms of, for example, how frequently the sensors can collect data and what type of sensors is needed based on the desired application. Also, the microcontroller can be used as a general-purpose microcontroller that can be utilized by students, teachers, and hobbyists in any application. In the conventional technology, an IC consumes power whether it is or is not in data transmission operation. With the technology used in this project, the IITUC8K1612 only transmits a continuous wave at a short period, which is during data transmission. Now let's go back and take a closer look at how the WSN works. The WSN consists of 3 ultra-low power sensors, such as pressure sensor, humidity with temperature sensor, and the ambient light sensor. The IITUC8K1612 chip is pre-programmed to read the data from the sensors. A stackable header is used for access to the sensors and the transceiver boards. The transceiver board is equipped with the analog devices ADF7024 transceiver IC with a 433 MHz chip antenna. It allows wireless transmission of sensor data to a gateway.
Okay, so by the way, participants, please stay. Please do not leave because we will be resuming our second topic this 3 p.m. and we only have 1 minute left before the second presentation. All right, thank you so much.
Once data from any sensor node is received, the gateway is configured to transmit the data to an HTTP server. Multiple nodes can be networked together and placed in various locations of a building to monitor the surrounding environment. This allows data to be displayed in the mobile app. It shows the information in each of the sensor nodes, such as the sensor node's ID, location, battery level, as well as the readings of the available sensors. Here, we can see the temperature, humidity, pressure, and ambient light readings. To scan through the other sensor nodes available, we click on the arrow buttons. Information such as the RSSI, the timestamp of the recent data, and the status of the node, whether active or inactive, is also displayed. Clicking on a sensor reading shows a graph of the historical data of that sensor, along with the timestamp of the data points. If you long press on the graph, an option to clear the data will show.
Okay, time check. It's 3 p.m. So, by the way, for the information of everybody, so today's session is composed of 3 topics. So we're done with the first one. So there are still 2 more to go. Okay, so please do not leave our webinar. So attendance check, we have 233 participants now all over the Philippines. As we can see from the chat box, there are a lot of participants putting their names and their locations, where they're from. So, okay, so to proceed with our second topic, so let me introduce our second speaker. So our second speaker obtained his bachelor's degree in electronics and communications engineering from De La Salle University, Manila in the year 2009, where he was given the most outstanding thesis award for electronics and communications engineering. He worked as a senior LSI development engineer, formerly known as design verification engineer at ROHM or ROHM LSI Design Philippines, Incorporated way back 2010 to 2016. During his time with ROHM, he handled 4 development projects and was the first engineer in ROHM LSI Design Philippines to undergo training in motor driver IC design in Kyoto, Japan. He also pioneered the 3-phase motor driver IC development in ROHM LSI Design Philippines. In 2017 to 2018, he worked as an IC design engineer at CDIA Corporation Incorporated, Philippine Link and United Solutions, where he switched his interest to USB technology ICs. Later, in 2018, he joined Analog Devices Incorporated and is currently holding the key role as a senior analog IC design engineer, where he focused on designing low dropout regulator ICs. So let's welcome our second speaker to present the topic, the IC design flow by Engineer Loelle Erico Altarejos. Sir Loelle?
Hi, hello. Can you hear me clearly?
Oh, yes, sir. Yes, sir.
Okay.
Clearly.
And then can you see my screen?
Yes, opo. We can see your screen already.
So, okay. So good afternoon again, everyone. So I'm Loelle Altarejos again. I'm an analog IC design engineer and working in analog devices currently. And this afternoon, I will be discussing the IC development flow. So earlier, Sir JM John Michael Gorospe discussed the LDO. So that was a more technical discussion. So right now I'll be discussing a more flow of how ICs are made. Let's take a look first at the overview. So in this session, I'll briefly discuss what an integrated circuit is. Then we'll take a closer look at each of the development stages. So there's a lot of them, from feasibility design, feasibility study or customer request, going to design, to layout, fabrication of the wafer, package assembly, PCB design and assembly, design, evaluation, and test development until release of the product. And we'll see as we go along, we will discuss and be tackling the different engineering roles or functions, or I may say the people involved for each stage. Okay, so there are so many terms or words that are really technical that can be associated to an IC or integrated circuit. The words you see on the screen are just a number of them. It's so complicated, right? An IC can be a linear regulator alone or a switching regulator alone. And when you put those two together, add a digital block and some control, then we have a PMIC or a power management IC. And you would also normally hear from other people that there's a lot of or thousands of gates in there, that IC. But what does that really mean? Or has anyone here experienced that somebody who is a non-ECE or let's say a non-engineering person ask you what is an IC or what did you answer or what would you answer. So I usually experience this during family gatherings. No, people would usually ask me, "What do you do? What's your work?" So I would usually answer just answer, "I design microchips," and that's the end of conversation. So there's a lot of definitions of what an integrated circuit is from these media sites, but I think it all boils down to the definition that an IC can function as an amplifier, regulator, oscillator, microprocessors, and many more other functions actually that has anywhere from hundreds of to millions of transistors, resistors, capacitors, even diodes integrated in a small chip. And here, what are these importance of ICs? So just imagine a world without integrated circuits. These ICs has already lots of applications, and there has been lots of technical advancements made throughout the years. For these applications you see on the screen, for consumer, your cell phones, your laptop, for aerospace, healthcare, military, broadcasting, transportation, and telecommunications, and many other applications. Also, ICs give us smaller size solutions. So have you noticed that a car's dashboard or the car itself doesn't get bulky even when the car's functionalities are adding up? For example, a radar modules nowadays are installed in a car for automatic lane assist, automatic opening of the trunk or hood, and technologies like that. And they're low cost. Maybe not all the time, but I can say that ICs can get quite expensive, but for its advanced functionalities, I'd say it's worth it, or the cost already is I don't care. So now here's the very colorful IC development flow. Here are different IC development stages from feasibility and customer request, design layout, and I put here the wafer fabrication a bit outside the flow, since usually this is outsourced, and also the package assembly. Go to the PCB design and until release. Again, I'm an analog designer, and the first thing that may come to your mind is that my role will be heavily here in design stage. But as a designer, you will need to work with other people with other roles like layout engineers, evaluation engineers, test engineers, etc. But make note that my experience comes from different companies, and not only designers will experience that working with cross-functional teams, but almost all of the people involved here will religiously work together. So again, my experience comes from different companies, but I'll share with you the IC development flow of this more generic and what is common. Also, I'm not a master of all of these development flow stages, because for each development stage, there are jobs or roles and functions that will be specialized on that stage. But I'd say that I have really worked with most of these people and got experience from them, and that is what I will share with you today. And then later on, we will also see as we go along that in some stages of the IC development flow, there will also be mini loops or mini flows in each of the stages. For example, there's a need to go back to a stage before going to the next stage. Okay. So first would be the feasibility or the customer or a customer request. Development of integrated circuits can start from an idea which needs feasibility. Is the first one. A feasibility study before being approved, or before pushing through to the project. And then the other one is a simple customer request. this is the most common usually what happens in the industry. So a customer talks to the AFAE, and then the business unit managers approve it, and then the project pushes through. Okay, so the people involved here, you will see on the upper right in this stage would be, of course, the business unit managers for the approvals, designers, layout, engineers, eval, test will also be here for some initial simulations, chip estimations, testability discussions. FAEs, or the field application engineers, will be the one of those who will be playing the key roles here, because they're the interface of the company to the customers. FAEs are technical and business-minded people. They would know the needs of a customer. If the customer needs an IC, they will be the one to be on the they'll be the first one to be on the doorsteps of the customer, discussing with the customer that we can do this, we can do that. If you want this, if you want that, and so on. And of course, the very important part is the customers. These people will give us money. Again, just an example of an idea which needs feasibility. A quick example is a comparison of what is out in the market. So before pushing through a project, sometimes we need to consider what we can do or what we need to do. So for example, in this table, listed is, for example, is an LDO datasheet or datasheet parameters. For competitor 1 comparing to competitor 2, competitor 1 is more superb, comparing its lower operating supply current and a better dropout voltage. And then, so eliminating competitor 2, competitor 1, comparing competitor 1 to what our company currently has. This is just an example. So competitor 1 still has a more superb operating supply current compared to us, but we can offer better supply rejection ratio at 1 megahertz. So what do the people need, or the market really need? So what we can do is we can do all of this, or choose 2, choose 3. But what we can do and what we can project is a more lower IQ LDO, or let's make an LDO which gives output voltage which is variable, not only one voltage. Let's do an LDO which has a lower dropout voltage, better load regulation, and maybe a more higher PSRR. Or maybe an idea wherein you will build an entirely whole system, or this is an invention, if I may say. During feasibility, so some questions to ponder. Will it generate income? I mean, the project that you want to do, the IC product you want to do, will it generate income for the company? How much is the full factory cost? So we're talking here about manpower cost, wafer cost, etc. Have you considered all of those? But the important part really here is, will it generate income for the company? Is it really doable? That is why there is a need to do initial simulations, consultations with other departments like layout, test, and evaluation. So other rules can also prove that this feasibility or this project you want to do is doable. So the schedule, what I mean here is, at the time of the release of the product, is it still needed or in demand? And do you already have your target customers? Does this align with the current trend? Or if you still don't have customers, who will be your FAEs to talk to? Actually, some ICs can also be under general purpose IC. I think everyone is aware of that. General purpose IC category, meaning they're not specifically made for a customer, but the general public can use it, but depending on their needs. So the other one is the most common, wherein a customer request is received, and this is just an example of a customer request. For example, our company will get This is an example, a customer supply that they're trying to build, a power management IC that they're trying to build, and then they will be requesting, for example, 2 LDOs for us to develop, one with 1.8 volts, 50 milliamperes capability, and the other will be 5 volts, 100 milliamperes capability. So, and then they will already give us the data sheets, and these data sheets are really important, I may say, before proceeding to design stage. Data sheets could be complete already before proceeding to design stage, but sometimes worst case can happen that data sheets are still in progress while design is waiting or starting already. So next, after that idea or a customer request, we'll now proceed to design. So meanwhile, mentioned a while ago is the importance of datasheet specs. This is what the designers will study and apply in their respective skills. And their main goal is to design and meet the specifications. The specs shown here is only an example. I can show it to you guys because this is already a released product. This is only an example that shows analog, unfortunately, only analog parameters. But in a complex world right now, ICs contains both digital and analog blocks. And one should expect that datasheet parameters are very numerous pages, not only analog, but both digital and analog. And this is also the stage where designers are building the schematics, the codes, thorough calculations and simulations are made. The people involved here are analog design engineer, digital design engineers, and MS verification engineers. And then the analog design side, so those guys are more of this schematic entries, and those digital guys are more into RTL coding. So for the analog design, so analog design engineer, that's my role. We take care of the analog design side of the IC. So we design from small building blocks of the analog, which namely current mirrors, amplifiers, switches, band gap, up to the whole function. Sometimes regulators, EDCs, DACs, even oscillators. We also design protection circuits for our system, like thermal shutdowns, overcurrent protection, under voltage, and many more. Here's just an example. So Sir JM earlier already discussed the LDO, but again, an LDO is a analog block that regulates the output, the Vout, at a given I load range, and it consists of an error amplifier, feedback resistance, and the pass fit. So as an analog designer, you should know how to balance things like for the pass fit, how much area will you use, how much dropout voltage will you be able to cater given your PSRR or your area once again, and many more like IQ, output voltage accuracy. Do we need trim? How do we improve load regulation? And then how much current limit do we do, and improving the PSRR, and many more actually. And analog designers will work closely with layout, even the evaluation guys and those test guys. And the end question after thorough simulation, after your design, will be, did you meet the specs? Just to give you an idea of what analog designers are doing. So the very first thing is the schematic entry. So a popular tool used here is Cadence Virtuoso. So schematic entry is where we put on our schematics. If we have already chosen our architecture, the schematics depend on what the designers think is best for the design. Like sizing of the transistors, architectures, value of resistors and capacitors. Once the entry is done, it is when we build simulation test benches. So this is where we put voltage sources, I biases, other stimuli are put, and then we perform thorough simulation for each specification or data sheet item. Simulations like stability sims, transient simulations, and DC simulations are done. And then why did I say thorough simulation? So in a simulation suite like this table here, we need to simulate lots of quote unquote cases or corners, I can say, because we need to simulate our design across PVT, that is process, voltage, and temperature, and all other conditions. Like for LDO, we need to see how the LDO works across I load, C load, and others. And we need to make sure that our design meets the specs. If not, then we redesign once again. So to give you an example of a simulation suite here, for example, we have a 3 processes times 3 V in, 3 temps, 5 I loads times 2 I load. This equates to about 270 cases. And sometimes these cases reach thousands actually. So there's a lot of simulations to be done. And what I want to point here is we vary the V in, and then the process is varied, and then the temperature and so on until we reach those 270 cases. So some companies actually use ADXL for simulations. Some create their own proprietary simulation GUI. Analog designers will also simulate LCKT sims, or in layman's term, these are the simulations using netlists with layout parasitics. We will tackle this later during layout, but yes, we need to resim our simulation suites once the layout is already done. Also, analog designers use in simulation models, and which greatly depends on process nodes. Process nodes like TSMC 40 nano, Global Foundries 130 nano, and many others. So now let's go to digital design. Again, nowadays there are so many complex systems in a chip. ICs are now called actually mixed signal ICs, that they contain very large analog and digital blocks. And here's just a simple example of a digital function wherein an analog block, a thermal shutdown block. This is an analog block which detects if the junction temperature is already high and reaches a design threshold, it will output a 1, and the digital block will output a 1, logic 1 to these regulators. So what does, I mean, with all of these questions here, so what will a logic 0 or 1 output from the thermal shutdown mean? What will the thermal shutdown block do to the other blocks once the junction temperature has reached the thermal shutdown threshold? Or is there a timing, or how many seconds will the regulators be shut down after a thermal shutdown fault? So all of these questions will be answered and will be detailed in a digital block. If there are timing constraints, what timing constraints and what outputs do we need from an input from an analog block will do. The digital block will take care of that. Some common digital functions in the industry. So inside of digital blocks are timers, synchronizators, resets and interrupts, and the popular I2C interface. Under digital design, there are 3 key roles to achieve a fully functional and spec-passing digital design. So first is a digital design engineer, wherein these guys, there are the RTL coders. They focus on that RTL coding. And then in parallel with that coding, the digital design verification engineers are the ones who ensure that the quality of the design are according to specs, and they do that by building test benches, creating and debugging tests, and they usually expose issues and bugs. When I heard about this role, I thought that digital design engineers do their own verification, but it was explained to me that if so, there's no bias in their design. Some other people, so here's the digital design verification engineer, they'll be the one to expose the bugs or thoroughly verify the design of the digital design engineers. And also, for the implementation, we have the design implementation engineer, wherein they will be the one to convert the RTL to GDS. They will be the one to coordinate with layout people. And remember earlier that I mentioned there can be mini loops or mini flows inside a certain stage. Here's one example of them. For example, an example would be a digital design engineer thinks his or her design is already done. So he already gives her RTL code to the implementation engineer. But once implementation is already done and parasitics or layout constraints are applied, they saw some timing constraints. So digital design, the design will, the code will go back again to the digital designer and would need to fix that. And in parallel with that again, verification should also be done. And that flow or loop will just repeat until the design is really robust. So here is just an example of a digital block, an output of a PNR, place and route, or an RTL to GDS conversion. And once we zoom in there, you will see logic gates. So that's why we say there's thousands of gates in an IC. And that's because mainly of sometimes of digital blocks. Okay, so the tools used for by digital designers are SimVision for the waveform analysis, GVim and Emacs for the RTL coding. So again, going back to this image, so since analog design is done separately from digital design, I mean analog designers are way too focused on designing, achieving specs for analog blocks, and digital designers focus on digital blocks. How do we make sure that the communication between these two works, these two worlds work? That is when the analog mixed signal guys or verification comes in, which is analog AMS verification is really needed, and analog mixed signal verification engineers do this for us. And they do really have the knowledge on both analog and digital functions. And their main goal is, yes, again, to verify and make sure that these two worlds here, analog, digital, are working harmoniously. They need to create verification plans, and they work closely with us. And then they do mostly top-level simulations. Okay, so design reviews. After doing all of your arduous designs and making sure everything is on point, everything is on target, that doesn't mean you can immediately move on to the next stage. One of the critical items of each development stage, not only design stage, is the design review, or some may call it peer review. Design review, again, is not only done during design stage because of its name, design review, but at almost all development stages before moving on to the next. This is critical because an engineer which will hold a design review of his design or of his, for example, a test board, might have missed something during his design, or that can be detected during a design review. Or there are things that an engineer thinks that a result is okay or working properly, but actually it isn't. So that can be also detected by the design review. So this stage is very critical, and it is done and needs approval before moving on to the next stage. The content of the design reviews will include results, findings, even issues you may encounter that needs more minds to brainstorm, or any necessary documents that needs to be reviewed. Participants can be from the engineer involved, and even sometimes customers can join actually. Because after design, layout stage is up next. So from my experience, layout can only start once the entire design is done. But also there are times that layout can be done in parallel with design if there are blocks that are readily available to be laid out. But what is IC layout? So what IC layout is just a process of creating an accurate physical representation of an engineering drawing. This is our schematics that conforms to constraints imposed by the manufacturing process, the design flow, and performance requirements shown to be feasible by simulation. That's what designers have done previously. From schematics we have during our design, it is now created to a physical representation, which is called the layout, and later on will be used for fabrication of our silicon wafer. CAD tools or computer-aided design tools are used to draw these representations, and the very output of this layout stage will be a GDS file or graphical database system, wherein number of mask layers or layout patterns are generated and to be ordered and to be sent to wafer fabrication for the fabrication of the wafer. So what I shown here is just a quick sample of a layout, wherein a PMOS in schematic, we will see this symbol. It has a gate, source, bucket, and drain. But in layout perspective, we will see and we'll be working with this kind of images or graphical representations. For in top view, this is the top view of PMOS. And in cross section, this is the cross section of the PMOS, wherein a PMOS has an annual mask layer, a P plus diffusion mask layer, N plus diffusion mask layer, poly mask layer. So those are the layers that will be ordered later on in wafer fabrication. So just to show you here an LDO pass FET. So an LDO pass FET is a power device. Oh, it's really big. Sometimes we have hundreds of parallel of LDO of PMOS just to produce a working LDO pass FET. This is how it looks like actually in layout, wherein all of your I load or current loads will be going through there. And here are just some examples of layout equivalents of schematics. We have diode, resistor, MOS, BJT, and capacitor. Again, I mentioned earlier that there can be mini flows, right? So here is another basic flow of layout, which starts from data preparation, where they receive the schematics from designers, which contains layout indications like what do we need to be matched, what nodes that needs to be taken care of, like shielding, what nodes do we need to be that thick or that not thin. And then this placement, the placement for lower hierarchy blocks or floor planning, what we call floor planning for top level blocks, is like planning where to put your living room or dining room in your house. This is where you decide in what coordinates do I put my housekeeping blocks, my PASFET, or my air amplifier. So devices and blocks are strategically placed during this stage. And then once strategically placed, the routing will be done. This is the wiring or interconnecting of devices. And then it will result to a final layout. But before that, layout engineers actually will do lots and lots of verification checks. They will run DRC or design rule check checks, LVS or the layout versus schematic, etc., and many more. Once they pass those and get approval, then that we can say is the final layout. So the guys who are involved here are layout engineers, and my experience, usually they're called in various designations. They can be called IC mask designer, IC layout designer, analog layout designer, but they're just the same. And they do, and what they do is just the following, are the same and just are the following. They're the main interface between the schematic design and the manufacturing of silicon die. And as mentioned earlier, they are the people who create the physical representation from the schematic. So here are some layout engineer essentials. So an analog engineer should be able to lay out block level or top level. They do floor planning and area estimation. They do layout design techniques like the one I mentioned, like matching or what needs to be shielded. They are really knowledgeable of the process nodes and the design rules of the process nodes, because design rules of each process nodes, like 40 nanometer, 180 nanometer, 130 nanometer, are different from each other. So they are knowledgeable of that. They are also they should be capable of negotiating with circuit engineers for any corrections and improvements. Tape out, we'll discuss this later. And here are just some notable essentials for a layout engineer. They should know how to mitigate these issues like latch up and these others. So again, the layout engineer will really need to work closely with the design, because of the layout indications will come from the designer, like the matching, noisy lines, and then the nodes that needs less parasitics. So here is again a feedback or loop going back from layout to design, because layout engineers should provide design engineers LCKT or LPE, whatever companies call them, but these are the net lists with layout parasitics already, meaning it's time for the analog designers to simulate once again and see the effects of the layout parasitics and make sure that these parasitics, with these parasitics in the netlist or in the design, the functionality of this design does not degrade and still complies with the desired targets. So what are parasitics? So I just gave here some example wherein for example, a metal 2 is right directly above metal 1 in layout, which creates a parasitic capacitor here. So what if that metal 2 is a noisy line or a switching line? So that noisy line will be coupled to metal 1. Are we sure that it is okay that this noise here will be coupled to metal 1? What if this is our input to a differential amplifier? So our output will be greatly affected with that. Or long routings in large chips, so they're really long routings. We expect long routings, so there will be parasitic resistances or large resistances throughout our routings. So are they okay, or are we okay with that? So we should check that in our design. These parasitics are not captured during schematic design, and actually they're responsible for a number of different types of electrical failures. Tape out. So Not sure why it's really called tape out, but for designers and verification engineers and for the layout, whether it be analog or digital, layout actually is the sweetest word you want to hear, because this means that the milestone, it's a milestone to achieve. This means all design layout are done and ready for fabrication. The GDS file is already sent to fabrication, and all design reviews are finished and approved. That means we are ready to go, and we'll wait for the silicon to arrive. Okay, next would be, what is a mask layer? So a patterned layer associated with semiconductor integrated circuit. Actually, sometimes we we normally use different process nodes, right? From 130 nano, 430 nano. The number of mask layers will differ also, given those process nodes. And the tools used for layout is Cadence Virtuoso, and on the left here will be your mask layers. So again, given the early example of PMOS, in a PMOS, we have an annual mask layer, P plus diffusion, N plus, and poly. So here are just some example of mask layers that will be ordered for wafer fabrication. So when layout is done and reviewed and tape out is achieved, mask layers and the layout pattern file, GDS file, are now transferred to the foundries or semiconductor manufacturing companies for fabrication. And after that, wafers are actually packaged. So during fabrication, usually in the industry, we call it wafer fab, where this time around the layout GDS file is already received by the foundry. And here are some notable foundries or semiconductor manufacturing companies, namely TSMC, or the Taiwan Semiconductor Manufacturing Company, Samsung, Global Foundries, and UMC, or United Microelectronics Corporation. Though some companies that design their own chips have their own foundries, but that really depends if how stable or robust their models are already. So to show you here just some different processes of the fabrication of a wafer. So how I imagine it is just like etching a PCB, but in a more technological way, because we're bombarding ions or ion implantation. We bombard P-type, N-type materials to create P-type and N-type materials in our silicon wafer. But our wafers, they undergo polishing and then oxidizing, and then we transfer the circuit pattern or the layout we have onto the wafer by lithography and etching. We bombard dopant impurities by ion implantation, and then getting annealed by diffusion. The process like this. I haven't really worked inside a fabrication or wafer fab, but during college, this I think was discussed. And with these processes and capabilities of foundries, then the result will be a wafer looking like this. And then our layout or the GDS or the mask layers we ordered are imprinted on those wafers. Usually, wafer fabrication process will take around 2 months. But again, that will always depend on the process node. What I know is the smaller the process node is the longer, I think, the fabrication time. So after the wafers are done, wafers will be cut or diced, and each chip or wafer is packaged where there are several kinds actually of packages. Packages can be chosen depending on applications, number of pins needed, or the allotted area or footprint for it. So you can imagine your diced or your wafer that is already cut here in the middle. and the pads already bonded to the lead frames and pins. And these pad placements also were checked during layout. Assembly process will I think, take around 1 to 2 weeks, depending again on the type of package. So yeah, I mentioned the wafer will be diced, so they will be cut. Then they will be attached using an adhesive to the lead frame. They will be wire bonded and then be molded to the end product of this. Here are just some examples of IC packages. So now, after the wafer fab and package assembly is done, meaning the IC is now ready to be evaluated or tested. But before that, we need different kinds of PCBs or printed circuit boards for us to be able to proceed to evaluation and testing of the IC. So we now go to PCB design. Actually, PCB design does not really need to be seated here, because it can start during design or layout, just make sure that the package of your IC will not change. But I usually put it here because the PCB will be of no use if the IC is not yet ready. Because in this stage, we'll be assembling also the PCB, so that we can proceed to the next stage wherein we will test and evaluate the IC. So PCB design and assembly, these boards will be used for design evaluation and test stage, which we will discuss after this. Actually, we have I think three kinds of boards, if I'm not mistaken. We have evaluation boards to be used by evaluation engineers, application or system boards used by application engineers, and ATE boards or automatic test equipment boards to be used by test engineers. So once the ICs are ready, after fabrication and assembly, those ICs will be mounted here, but sometimes boards are socketed, so no need to be soldered. The ICs not need to be soldered. And this PCB design and assembly, actually they can be outsourced, but usually semiconductor companies have their own PCB design capability. The one that is usually outsourced is the PCB fabrication. And the people responsible for this is, of course, the PCB design engineers, and they will be the one to work closely with the evaluation team, test team, and even with analog designers to put up these evaluation boards. And they ensure that the PCB parts availability or the bill of materials accuracy are okay. And also the PCB vendor management. They make sure that the delivery is on time and they will get high quality boards. The tools used, I think, the tool used is Cadence Allegro for PCB design. So now let's go to the next stage, which is the design and evaluation and test development stage. Because after the ICs are ready, all of those design, verification, layout, we have done. And after waiting for about 2 months or more for the wafer fabrication to be finished and packaging to be finished, it is time actually for the moment of truth, because it is now time to see if the IC is really functioning as designed or as expected. And time to move. It is time to prove to customers that all specs and all that we designed are working or they're according to what they wanted. So design evaluation. This is the stage where functionality of the IC will be thoroughly evaluated through bench testing. And all the parameters during design, all of those simulations we did will be tested now, will be evaluated now, but using real instruments, not simulation test benches, but real laboratory instruments. And then if you remember during design stage, yes, we check all functionalities, though now it's time again to check those, but with the physical IC that we have right now. And the entire evaluation stage will actually be directed by an evaluation matrix, wherein this matrix contains what parameter we need to evaluate, what V-in conditions do we need to test, what conditions we need to apply, like the eye load and temperatures. Also the priority list you will see, because sometimes the customer would want to see this first before this, something like that. And here's an example of an evaluation test bench where you could sweep V-in and monitor the output voltage or the ground current. Or sometimes you can sweep the temperature also by using a temptronic and measure the output voltage and also the ground current. Simple setups, some are simple setups, but most of the time they can be as complicated or even worse than this. And have you noticed these plots or waveforms on the right, wherein if you try to buy a product or an IC and then you check the last parts of the datasheet specs, you will see some waveforms in there. These are the results of the this design evaluation stage, where it shows the performance of the IC. So the people involved here are design evaluation engineers and apps engineer or applications engineer. In some companies, they don't have really apps engineer, but design evaluation engineers acts also as their apps engineer. So these people are they do the bench evaluations. They also work with the PCB engineers for the board design, and work with others like test engineers also, and with us, the designers, if they have a question about the setup, the result they're getting. And the difference between design evaluation engineer and apps engineers, that design evaluation engineers usually evaluate the internal specs of a chip, and the applications engineer evaluate most on the application side, like the ones that the data sheet parameters are showing. And also the application engineers, they have an extra role of, they support the products on a website. Like for example, if a product is already released and end users have questions how to use the product, so they do that. They do support that. And these guys are, and these two design evaluation and apps engineer, they're really knowledgeable how to use different kinds of laboratory instruments, namely oscilloscopes, DC sources, the thermostreamers, and many more actually. And usually companies differ on the approach. Sometimes they use different instruments. Also, they use different softwares. Like some other companies use LabVIEW for the automation. How do you control the instruments and to get plots out of the instruments? Some other make their own automation, their proprietary automation. So the other one is the test development. The test development activities also would usually start as early as design. That is the development of test specs, test boards, and planning. But this is where the testing of the IC or actual testing is done. Test development is the bridge or the very critical part of the development flow, because it is the bridge to production or manufacturing and release of the product. This is where test solutions are made. Test solutions, I mean the test hardware, test program, the test specs. And I'd say it is a bridge to production or manufacturing, because test development will emulate what will happen in the production from wafer probing until final package testing. And ATEs, or if you're familiar with this, the automatic test equipments, will really play a big role in this stage, since they are capable of testing wafer levels and final package units. Some of you may ask, what is the difference of design evaluation, the stage I discussed earlier, from this stage, which is the test development, since we are also quote-unquote testing or evaluating the IC during the design evaluation stage. But the answer to that will be, in production, we wouldn't want an evaluation engineer or a number of evaluation engineers to sit down on a bench and measure all parameters for thousands of, even millions of units ordered by a customer. And what we would want to happen is, we want that testers will do that for us. So there's automation in there. So what we want to do is to have a test hardware or test board and test program for our testers. And our testers will be the one to tell us if that unit is a pass or a fail. Pass meaning after a unit undergoes the entire test program, nothing fails. And a fail meaning a reject. After the unit undergoes the whole test program, fails even one parameter, then it will be a reject. These ATEs actually contain numerous meters, oscilloscope, DC sources inside it. So it's like evaluating automatically numerous or a number of units in production. So the people involved here are test development engineers. So they build test hardware. They build the hardware, the test boards, and the software, the test program. And they evaluate the robustness of their test solutions. They're also capable of, like the design evaluation engineers, they're also capable of doing bench testing. This is for them to correlate their results in their testers. And then, of course, they will work hand in hand with us, also PCB engineers and eval engineers. And another thing is they are also the ones to prepare the probe card. The probe cards are those, here is an image of it. These needles here will be the one to probe a wafer level, a wafer, and test it. The ultimate goal, or there are two ultimate goals for a test engineer actually. So one is to decrease test time, because a decrease in test time, that means lower cost, because of lower electricity costs or manpower cost. And they need to achieve the desired yield. Sometimes it's 95%, sometimes it's even 98% yield. And during yield analysis, they will be able to answer these questions, like what test parameters are failing, why are they failing, is the unit really defective, or do we just need to alter and correct the test program setup? Because in a wafer map, so here's an example of a wafer map, the red ones here are fail. So just from this image, we can say that this is a low yield. A yield is the number of passing units over the total units. So from this is a low yield, and test engineers will make sure that why are these parameters failing, or it is just a setup problem. So questions like that needs to be answered by the test development engineer. And they also test final package. Test development engineers for yield analysis, I think they use Pareto diagrams and histograms. And these tools also differ across companies. they also use some proprietary tools for yield analysis. Now we go to manufacturing or release. So it is somehow similar with test, and this is only a transfer to a test development hardware transfer to manufacturing stage, because the test hardware that was developed during test development stage, the test program, the test specs, once they're okay, once they're reviewed, they will just be transferred to the manufacturing or production stage. And the people involved here, the product engineers, though they will work closely with the test engineers, and the product engineers will, of course, be knowledgeable also of the test solutions that the test engineers have made, and they will provide 24/7 manufacturing test support. They will continue to drive yield improvement, and they really play a vital role in keeping the manufacturing floor up and running. Time check. Okay, so this is just a quick, maybe in a nutshell, of from a customer order until to how we ship to the customer the chips that they ordered. So it will start from a wafer, then the wafer will be probed in a wafer probe system, and all the rejects will not be packaged. Then once package is done, the final packages will be tested in a tester, and all the rejects will not be shipped to customer. And that's just a simple flow of once a order of a customer will happen. One question that may arise, or not all developments will be perfect or smooth. One question would be, what if something is out of spec? So for example, an LDO, this LDO parameter does not meet the spec, or this parameter is way out of what we expected once the IC arrived in our laboratory. So this needs a respin, or that may result to going back to the design stage and to do some investigations. So what really happened, or what things have we missed, or what things do we need to do to improve our product? Yes, it will be costly in terms of money. So because the mask layers we ordered in layout, they're really costly. So if we need to change some design schematics in there, for sure layout will change. So we will order again mask layers, and of course manpower cost. Instead of people doing another project, people will be tapped again and redesign the product. Costly also for the delays. In this case, we need to negotiate with customer. What could be done, or what can we do still to satisfy our customer. And before I end, some more roles I want to share with you that can be inserted anywhere in the development flow is the firmware development and the failure analysis. So for firmware development, of course, firmware and software development will always be there. And actually, it can be needed anywhere in the development flow. Sometimes we need firmware for our simple automation GUI, and it can also be a firmware needed for company's product. Actually, firmware developers in our company also do firmware kits that are sent to customers together with the IC for the ease of use of this product. And lastly, the failure analysis. So I wanted to share with you this because these guys also play a really vital role in the development, because once we release the product or sell them to the customers, that means we already made money. But it doesn't mean it stops there. We need to support returns, or these are the products that are released but deemed to be defective or determined as defective by the customer. So the failure analysis, actually, the main goal is to determine and understand the failure mechanism and the root cause of the failure. So also this team, the failure analysis team, they're like a service provider to the whole company, because anytime that we need to decapsulate an IC or to see the inside of an IC from a microscope, they'll be there to assist us. And of course, the customers will be very happy once they return some ICs. They will be very happy that we show them support, or we show them analysis why these ICs were released but were defective. And failure analysis engineers, yes, they perform FA procedures like X-ray decapsulation and so many abbreviations here. But they also do bench testing. They're also aware of and knowledgeable about cross sections. And here's just some images that failure analysis engineers would usually provide us, like X-ray, SEM, LEM, and decapsulation. Okay, so what to expect in the semiconductor industry? So it is really cross-functional. We will be working with different people under different teams and specialties. It is quite nice to experience this, so you can be knowledgeable of other development stages. Your interpersonal skills will also be surely tested. We will also work with international minds, not only here in the Philippines, but you can get idea from people from other countries, high technological countries. And you will also be a part of the development of the latest and upcoming technologies, but with confidentialities, of course. It is challenging, but yeah, it's really worth it. That ends my presentation. I hope you learned something today. Thank you.
Okay, thank you, Sir Loelle. That was indeed a very informative presentation. So now we're going to begin answering the questions submitted during the presentation participants. So again, as a reminder, to the questions pane in your attendee control panel. So the first question, Sir Loelle, is from Sir Darwin Maniaga. So the question is, for a typical mixed signal chip, let's say, for example, a single channel 12-bit DAC, how much is the ratio of the analog versus digital block in layout's floor planning perspective? So would the ratio change if it is for high-speed applications?
Hello. Okay, so I have not really experienced designing DACs, but very interesting question. So what I usually see in DACs are just a little of analog, I think. So maybe more on the resistor ladder and more on the digital side. So I think yes is the question. If higher speed is needed, then a larger block could be needed for that. And then, but I think the important part for ADCs is also the accuracy. So, sorry, the number of bits you can introduce to your chip. So that also means you will need a larger block for that.
Okay, so thank you, sir. Next question is from the same participant. Is it a norm to perform power on simulating the chip's functionality across the VIN, rise, and on time?
Power on. Sorry, is it norm to? Yes. So we do that simulation. That I think that the one you're referring here is sometimes the power sequence, maybe, wherein we pulse the V in from 0 to some desired voltage, and then we measure the output maybe. But yes, we do that simulation just to check that everything is powered up sequentially or even powered down sequentially.
Okay, thank you so much, sir, for that answer. So the next question is from Sir Margallo. So we have here, latch up is the biggest issue in LSI. So is there a way to detect latch up during the layout design stage?
Yeah, so actually there is a check or a run by layout engineers about latch up. Not really familiar with that, but yes, we could actually do some latch up checking during layout. Actually, the P cells of CMOS already have guard rings in there sometimes to prevent latch up, and the models or the standard layout models that are given to us by the foundries have already considered the latch up. But when you put things together like in a really uh, big system, sometimes there can be some latch up there can be missed, especially when I work with motor drivers that latch up are very prone and cannot be detected easily during design and layout. But yes, it can be prevented by the latch up checking by the layout engineers. They do some runs there or latch up design rule check, I think.
Okay, so thank you for that, sir. And next question we have here from Sir Darwin Maniaga. So given the cost of the wafer keeps on increasing, are there any design or layout related improvements being done to lessen its impact to FFC?
Well, I cannot directly answer your question, but costs of wafer, yes, they are really increasing with the decreasing process nodes. But before choosing a process node, which is the most expensive process node is the lowest, the smallest. So before choosing that, you need to first consider your application. It doesn't mean that it is a smaller node, so it's the best, right? So and because it's costly, so you need to think of, for example, you're designing an LDO or a PMIC, then I think the best process there would be 130 nanometer because of the current capabilities of the metals there. But we will not directly use a much smaller node because it is really expensive. So again, you should go back to the feasibility and know that what is best for our design, for our layout, for our application, and just not decide that we will use a smaller process node for the sake of telling people that we use a very small process node. We should consider our application as well.
Okay, that is well taken, sir. So next question we have here from Sir Joseph Olieres. How does eval parameters related to test parameters? How it will help the product engineers to analyze the failures at test, either probe or final test?
Yeah, so honestly, the eval parameters are really almost the same with test parameters, but there are some limitations in testers. Like for example, if you're evaluating an LDO, you can evaluate PSRR on a bench, while in a tester, you will not be able to do that. So it is understood that the PSRR cannot be tested in LDOs, but can be evaluated in bench eval, and we should make sure that across all conditions, PSRR specs are met. So they're almost the same, but not all, there are times that not all eval parameters are to be brought to test parameters. And of course, it will help product engineers to analyze failures, because there are times that each of a single a single unit can function well and another cannot. So eval engineers can say that there is some, what do you call this, dependency on the bench setup or test setup, which can be a really very vital information to product engineers, that if I use a different tester or if I use a different instrument, this parameter will fail, something like that.
Okay, so thank you, sir. Next question we have here from Sir Margallo. How is simulation data compared to actual evaluation data?
Yes, so we sometimes get, I'm not sure if what's the term for other companies, but we usually get PCM data. I actually don't know the meaning of the PCM, but this PCM data will give, the foundry will give us the information that, for example, our MOS devices are slow. For example, our MOS devices, their VTH are higher than expected, or our PMOSes, the VTH are lower than expected, or resistors are fast, meaning our resistor values are lower than expected. So in that case, we have during simulation, we have simulated all of those corners or conditions. And when the IC finally comes to us or arrives to us, we will ask for that PCM data, and we'll try to correlate the result of the evaluation to our simulation using that PCM data and the information from the foundry itself. And we just really rely on the models, actually, simulation models of the different process nodes.
Okay, so thank you for that, sir. So next is, actually, this is not a question, but something like a positive remark about your presentation. So very concise summary of the IC development flow. Not really a question. I just think reliability or quality also plays important role in an IC flow. So there are responsible in doing stress tests such as a COL, ELF, latch up, ESD, and many more. So
Yeah.
next question. Yes, sir.
Good point, Darwin. Actually, I have a slide for reliability tests, though I might lack some information for that, so I decided to not to discuss those. But yes, the ICs the ICs we get, they undergo reliability tests like the one Darwin said, and ESD test, like we test the ESD, the pins for ESD test, and then some kind of high temperature. We soak the IC at high temperature at a long time, and then we check again if the IC is still working. So yeah, good point.
Okay, so there are still 3 more questions for this topic, sir. So you mentioned some tools. This is from, by the way, Sir Alvin Almenshon. You mentioned some tools about simulations. I am in academe and I want my students to use some user-friendly simulations for circuits and PCB layouts. So my experience at the moment are only ProShoes, ISIS, ProShoes, ARES, and multi-sim. So my question is, are these software enough, or can you suggest some more better tools for us to use?
Yeah, actually, that's a very common problem right now. Even even analog devices tie up with other universities. The tools, the licenses are still ramping up because, of course, they're costly. So maybe I can suggest, if you need maybe LT Spice, I think you can use that for simulation, because that is what is used by some students in who's taking up masters before. But I think it is really good, I think, to invest in Cadence Virtuoso.
Okay, so thank you so much for that, sir. So we will be having the last question, no, since we are running out of time. So we have here from Ma'am Joanna May Kinalayo. So what kind of simulation tool or analysis do you usually use for reliability on electromigration or IR drop?
For electron, both of these are really considered during layout. So layout guys do simulation tool also in Cadence for the EM and IR. So for the EM, well, in the perspective of an LDO, so it was discussed earlier that the PASFET, right, it receives most of the I load. So EM, I'm not sure if I can divulge the one that we're using in the company, but EM is thoroughly checked across that PASFET just to make sure that, for example, a 1 ampere I load is well distributed in that PASFET and not and will not burn some parts of the PMOS or some wiring in there. And then for the IR drop, yes, again, Cadence is used by the layout people to do the IR drop investigation, and then they will give them the results to us, and we will decide if it is okay or not. I mean, the IR drop.
Okay, so I think that answers the question. So, okay, so I think some of the questions here will not be entered. You can actually contact, right, sir? You can actually contact you if they have any more questions to us, because on time check we are here 4:21 p.m. So to mark our as a mark of our appreciation and gratitude, so we would like to present this certificate of appreciation to Engineer Loelle Erico Altarejos for having shared his knowledge and expertise on the IC development flow during the lecture series on Microelectronics Session 2, held at Zoom Web Conferencing on October 30, 2021 with accreditation number ECE 2009001223, signed by the IECEP IBC Governor Olga Joy Hirasta, PECE, and IECEP IBC Secretary Genevieve Catal, ECE. Okay, so wala bang virtual clap dyan from our participants? For our dear Sir Loelle for sharing his expertise to us about IC development flow. All right, so we have here a virtual clap. Okay, thank you so much, sir, for that very informative talk. Okay, so for the participants, all right, so okay, so we will proceed now, with our online quiz and evaluation for the topic presented by Sir Loelle. So participants, kindly click the link that I will be providing in our chat box here, or chat panel, to access the online quiz and evaluation. Again, remember, you are only given 15 minutes to answer it, and then we will start with the next topic of this webinar. So do not leave the Zoom meeting room, all right? So I will be posting now the link. Again, 15 minutes, and you are given only one chance to answer the quiz. Okay, one response per participant. Okay, God bless. And again, this will serve as your attendance and also the basis of your certificate for the CPD units. And then be back by let's say what time is it? 4:23, 4:38. So maybe 4:48, 4:40. Okay, 4:40. The link. Okay, I know. Wait. Sorry. So this is the link for the second quiz, for today's webinar. Okay.
The number of samples that the graph can show can be configured in the settings menu. The refresh rate, which is the interval at which the app will query the server for new data, can also be configured here. The user can also set minimum and maximum threshold values of the sensor readings. Clicking on the Set Limits Values will show a dialog box where the user can input these limits.
Okay, dear participants, kindly wait for a while, no, while our technical team still preparing some slight modification on the questionnaire. Okay, so we will open it and then I will be sending you the link if it's already ready for accepting responses from you guys. All right.
App is running in the background. The app will notify the user when the battery of the sensor node is low or when the limits are reached. The mobile app shows seamless remote monitoring of data from the deployed sensor node at any time and anywhere in the world through the internet connectivity. Wireless sensor networks can also be used in applications like smart buildings, smart agriculture, smart homes, healthcare, structural monitoring, transportation systems, and many others. Indeed, WSN has a continuously growing range of applications that help improve human lives up to the present day.
This is the Electronics and Communications Laboratory of MSU IIT. Inside are facilities and technologies that allowed us to design and develop communication systems for a wide range of applications. One of which is the system that uses wireless electromagnetic radar for groundwater detection. It is funded by DOSTP Shared. The project aims to first, evaluate the ability of electromagnetic waves to detect underground water, estimate its depth and quantity. Second, map areas with possible sources of water.
This program allowed us to practice and apply digital signal processing and RF engineering. These are knowledge and capabilities we gladly shared with our established network of neighboring universities around Mindanao through various training modules and exercises. This activity could be a basis for each of these universities to further their research capabilities in the field of electronics and communications that will eventually yield into more meaningful integration of electronics communication courses. Researchers get to collaborate with industry players to take the research product to another level of commercialization. This mindset has to change. They should think of making their product visible in the market and reach the end user via commercialization. Hence, MSU IIT partners with construction firm in Davao City, Iligan Light and Power Incorporated, Philmico, and Department of Agriculture.
The outcome of the program is in support to the goals and endeavor of DOST, which is to develop new technology and strengthen the capabilities of universities to conduct innovative research in Mindanao. Thus, research environment will help universities create innovative research and hopefully become world leader in modern wireless communication, microwave, and smart antennas by addressing the needs of industry, government, and the scientific community. It is just only a matter of time that the Electronics and Communications Laboratory will largely contribute to the worldwide modernization.
Being the pioneer and a leading institution to establish a niche in microelectronics integrated circuit design in southern Philippines, MSU IIT's Microelectronics Laboratory is leveling up its endeavor by engaging a system-on-chip integrated circuit design development. Over the years, it has been promoting innovation and awareness in microelectronics IC design in Mindanao by offering courses and trainings that will enhance and provide advanced skills to aspiring IC design and layout engineers in the region. As a result, the Microelectronics Laboratory has been producing
Okay, so I think the form, no, the Google form is already ready to accept your answers. So let me share to you the link again. Okay, so by the way, okay, so let's try again with the link that I've provided in the chat panel. If there's any problem or if it's okay now. Okay na. All right, sige. God bless on your quiz.
battery used for wireless sensor networks applications. This two-year endeavor is supported and funded by USAID STRIDE, a program that has the goal to stimulate inclusive economic growth by boosting science and technology research. Building upon the success of the inlay chip, the Microelectronics Laboratory took a major leap towards designing a system-on-chip solution for wireless sensor network applications, which is made possible with its funding agency, the DOST PSHIERD, the mandated Philippine Council in the implementation of strategies in the industry, energy, and emerging technology, research and development sectors. With its 3.5 years of implementation, the project started a modular approach in designing the system on a chip, which is composed of an energy harvesting unit, a power management unit, and a microcontroller. The modular approach lessens the complexity of the design and ensures an optimized and functional circuit performance. The final year develops a versatile system-on-chip design. The MCU, PMU, and EHU are combined onto a single integrated circuit chip, thus giving birth to the final product of the project, the IIT-UC8K1612 IC chip. The IIT-UC8K1612 chip will be utilized to develop a customized wireless sensor node, which is an IoT device used to monitor environmental conditions such as temperature, humidity, pressure, and light. The wireless sensor node is composed of 3 fully customized circuit boards. The top board houses the PV cell for the light energy harvester and the sensors used based on the desired application. The middle board includes the RF module, which is essential for wireless communication purposes. Lastly, the base is the main board, which highlights the IIT-UC8K1612 chip, along with the necessary external components. Located inside the chip are the 3 main circuit blocks: the microcontroller unit, the energy harvester unit, and the power management unit. The overall system works starting with the energy harvester unit. The energy driven to develop, innovate, and be the pioneers of research and development in integrated circuit design in southern Philippines, and to cultivate microelectronics IC design awareness in Mindanao, MSU IIT's Microelectronics Laboratory responded by designing an integrated circuit chip, a 3-year project funded by DOST with over a budget of 31 million pesos. One of the many key features of this microcontroller is its ability to tap into the telecommunication devices, which can further improve management systems. With the use of this developed technology, phones, tablets, or even the computers of individuals who enter the premises can be prompted to preview the necessary aid in the event, for example, that there is a need for evacuation or rescue. Aside from that, through the use of a network of sensors, the microcontroller is capable of monitoring an entire environment and status of an establishment or given area in real time. Data on factors such as temperature, humidity, and even the presence of physical movement can be processed and utilized to automate, say for example, the switching of indoor light or even air conditioning temperature control in an area. With the microcontroller's self-sustaining mechanism, it would enable industries and sectors alike to monitor, record, and organize data directly from the microcontroller. This way, sites or facilities are monitored 24/7 without the need to send personnel directly to the location, making the whole process greatly accelerated and undemanding. Smart agriculture can find an effective use of this technology by providing their facilities a more advanced method of approach concerning crop and environment maintenance. With the extensive and promising potential of this highly reliable technology, the way smart buildings, smart agriculture, industries, management systems, and sectors alike will be able to operate and function to a higher and better degree, thus paving a way to a more enhanced and progressive performance in the workplace. To cultivate microelectronics IC design awareness in Mindanao, MSU IIT's Microelectronics Laboratory responded by designing an integrated circuit chip, a 3-year project funded by DOST with over a budget of 31 million pesos. One of the many key features of this microcontroller is its ability to tap into the telecommunication devices, which can further improve management systems. With the use of this developed technology, phones, tablets, or even the computers of individuals who enter the premises can be prompted to preview the necessary aid in the event, for example, that there is a need for evacuation or rescue. Aside from that, through the use of a network of sensors, the microcontroller is capable of monitoring an entire environment and status of an establishment or given area in real time. Data on factors such as temperature, humidity, and even the presence of physical movement can be processed and utilized to automate, say for example, the switching of indoor light or even air conditioning temperature control in an area. With With the microcontroller's self-sustaining mechanism, it would enable industries and sectors alike to monitor, record, and organize data directly from the microcontroller. This way, sites or facilities are monitored 24/7 without the need to send personnel directly to the location, making the whole process greatly accelerated and undemanding. Smart agriculture can find an effective use of this technology by providing their facilities a more advanced method of approach concerning crop and environment maintenance. With the extensive and promising potential of this highly reliable technology, the way smart buildings, smart agriculture, industries, management systems, and sectors alike will be able to operate and function to a higher and better degree, thus paving a way to a more enhanced and progressive performance in the workplace.
Okay, so are all the participants already answered the quiz and the evaluation for topic 2? Because we will start with our third topic for today. Okay, I think you are done answering the questions, no? For the evaluation and the quiz also for which will serve as not yet po. Okay, so maybe I will give you 3 more minutes for those na hindi pa natapos no pag-answer. Just 3 more minutes. We will start exactly by 4:45 for the third topic.
Being the pioneer and a leading institution to establish a niche in microelectronics integrated circuit design in Southern Philippines, MSU IIT's Microelectronics Laboratory
Okay, so I think everyone is now ready to listen to our third speaker. By the way, regarding your questions about the recorded video and also the presentation from our presenters, you may email your concerns, no, in our IECEP email, which will be shared later on before the webinar ends. So yes, we have here the email of our IECEP Iligan Bay chapter. We have isep.iliganbaychapter@gmail.com. So for those participants who are interested in having the recorded video for today's webinar and also the presentation of our dear presenters, but still we will ask the presenters to share it to their files to us, for us to share their files to you guys. So now we will be proceeding to our third topic for today. Okay, so now we are on the last but definitely not the least topic for this webinar. So let me introduce to you our third speaker. So he received his bachelor's degree as an academic scholar in electronics and communications engineering from Mindanao State University, Iligan Institute of Technology, and he also has a master's degree in electrical engineering, major in IC design, obtained from National Taipei University, Taiwan. Currently, he is taking up his doctoral degree in electrical engineering at the University of Technology, Sydney, or UTS, in Australia. So he is also an experienced analog and digital IC design engineer at Service and Quality Technology Company in Taiwan in 2008 to 2010. Later, in 2010, he went back to the Philippines and worked as faculty at MSU IIT to share his knowledge and expertise in microelectronics and became the chairman of the Electrical, Electronics, and Computer Engineering Department at the College of Engineering last 2014. When it comes to research publications, he has received 3 Best Paper Awards in international conferences like IECEP and EU and SIDNET, and has a long list of published papers in IEEE conference proceedings and international journals. Like, it would take a lifetime for me to even briefly introduce to you what are those published papers are all about. So not only that, he is also involved in a number of multi-million research projects as a program leader and a project leader at MSU IIT, particularly the InLight research project funded by USAID STRIDE in 2015 and the recent MicroC-IC program, the design of microcontroller integrated with energy harvesting and power management, which concluded last October 2020. I can say he is in the top list when it comes to promoting microelectronics, particularly among the universities here in Mindanao. Without further ado, our third speaker for today, who will talk about the microelectronics journey in Philippine education, is no other than Professor Jefferson Hora. Sir Jeff?
Thank you, Rochelle. Thank you for the warm welcome. It's quite long introduction, but it was an overwhelming introduction, Rochelle. Thank you guys for joining in, and I guess everyone is still there. I've seen 217 participants as of the moment. To set the tone light, this is not really technical presentation. It is somehow just like a summary of all what you have learned on the past presentation last week and this week. So this also will going to set the tone, just like promoting the microelectronics education here in the Philippines. And of course, what are the necessary requirements or steps for the students to prepare yourself to be a researcher in IC design, at the same time to sell yourself to our industry partners, just like those speakers who share their expertise also from analog devices and SiNex semiconductor. SiNex design. So allow me to share my screen. Let me share the screen. Is my screen visible? Okay, thank you. So the title itself, Microelectronics Journey in the Philippines Education. So somewhat it is literal. All the slides pertains to this particular title. So I have set 3 major discussions for this presentation. So I'll start with the historical background, and in the middle of the presentation, allow me to walk you through on the previous and current initiatives done by the academe and the government, and including the industry. and how to move forward and the roadmap for this IC design settings here in the Philippines. So let me start with giving you on the global and Philippine situationnaire with regard to these semiconductors and electronics industries here in the country. So the Philippines, the semiconductors and electronics is largely, if you know, most of you knows already that the semiconductors and electronics are dominated by semiconductor industry or the semiconductor manufacturing services. And these electronic manufacturing services or the original design manufacturer is under or represented in the Philippines compared to the what we call as the SMS. So this SMS is the K upstream or the enabler to the rest of the industry of the semiconductor and electronics. So what you've seen here on the right of the slide, the semiconductor comprises the huge or the bulk of this pie chart. So it contributes around 73% of the task. So let us try to understand on the local IC design industry. So if you try to check, the local IC design industry only comprise 1 million of what we call as $1 million or pure service provider. So this will try to give you an rough estimate of 8 to 15 million in US dollar for the Philippine economy. So what we try to see here is it is still invisible for the global market. So for this amount of 82 billion, and it is reported in 2013, it's quite old data, but somehow it is quite growing up to this year. And the Philippines should be emphasized that the talent development on the analog, and of course not only to that, it also include the mixed signal and digital platform should be contribute to build a robust foundation for the IC design services. So we need to develop a local champion and promote this what we call as IC design, just like a capless, to target to target an amount of 50 million US dollar of annual revenue in the Philippines. So it's quite challenging because how to promote this IC design in the country, wherein we have been doing this since 2010. When I joined IIT, it was quite new to the university, and even if UP Diliman professors are trying to engage other universities to promote further these IC design sectors in the semiconductor and electronics industries here in the Philippines, but still up to date, it is not yet so significant in numbers, and that is why we could really tell that even if slowly growing, but still it is invisible in the global market. So why it is invisible? Because we need to check the three main criteria. First is there is a cost saving of this particular industry, and the time to market. Somehow we need to fast track to that because the technology is really fast evolving, and we need also to check the R&D flexibility. So that would be the third criteria that need to revisit by the industry with respect also with the help of the government and the academy. So the question now is how to position the country to be the center of this criteria. So that is why we are here and we are continue promoting so that we could really elevate this call and try to sell the Philippines as one of the Silicon Valley here in Southeast Asia. And we need to get a value proposition, and that is why we try to promote this, and we read this particular news brief or news article that the government tried to boost and try to sell the country that someday somehow there will be more companies will be coming in, not only local players, but those global or big companies in terms of IC design will come and join the workforce or the activities or the ecosystem in IC design. So there are a lot of news since 2011, 13. What we have seen here is 2016, trying to promote. Even Taiwan professors are trying to sell the Philippines that the next frontier will be the engineers of the country doing IC design. So our mission, okay, this is taken from the PEIC. The mission of the country is to position the Philippines as the key player in the global IC design industry ecosystem. So we need to try to establish a home base of competitive IC design, not only in terms of services, but really an R&D. So, and this will try to attract destination for foreign IC design related companies to locate the activities here in the country. So the long term is to sustain, okay, to sustain and rejuvenate the Philippines' future economic growth in semiconductors and electronics. So we need to accelerate the demand for IC design in the country. So how to do that? So we start with the academe and with the help of the government and of course the industry. So there's a target and strategy. So we need to be aggressive and fast track the targets for IC design. It was established the target in 2016 that there will be around 50 million per year US dollar. And it would be 600 fully operational designers. And the question right now is, are we seeing this number? Because it was 5 years ago, 2016. But we are still not seeing this. That's why it's a bit challenging up to date. And there should be more push coming from the university to help promote IC design and to try to adapt the curriculum in the bachelor level and up to the graduate level. So the medium term was set for 2020-2025. Okay, so it will try to generate hopefully up to 2025 of 310 million US dollar investment in terms of this IC design. Okay, and we need to revisit this one on the next 4 years in year 2025. So what are the previous and current initiative done so far? So let me try to start with the previous one. Okay? So in 2001, UP Diliman can have some projects called DCTI, and this is way of promoting and try to increase critical mass of students who will be engaged in IC design activities, and it will start from training of the faculty. So in 2001, there are few university joined in UP Diliman's call to try to increase this activity, and eventually 𝐼𝐄𝐿 was there since 2021 to help UP Diliman and try to promote to the students and adapt the IC design in the curriculum itself. So UP Diliman also tried to progress that one into creating and establish the microelectronics education. So it expanded with several universities. Okay, you've seen here De La Salle, Mapua. Also, we have also those universities in the northern part of the country. And it progresses to an IC program and expanded by DOST, and it was in the year 2010. And it is where 𝐼𝐄𝐿 got the very first license tool in 2010 through the IC program, and we own the one of the project of the program called IC, and it is the design of the what we call as ADC sorry, yeah, it's a DAC design, digital to analog converter, and it was lasted for 2 years. And UP Diliman created another one, and after IC, they call it Micro Education North or Micro Ed North. So they try to expand further the university collaboration in the northern part of the country, in Luzon area. So, and to summarize everything, it's still not enough. So that's why there's a bulk budget given by the UST under PSERG, and that is now the birth of the Philippine Integrated, Philippine Institute for Integrated Circuits. So that is the PEIC. So that was in the year 2013. So the PEIC initiative was to try to have this industry and academe join together, especially with the help of the government, to achieve the set goal for trying to increase further the critical mass of IC designer in the Philippines, so that we could really have some foreign industries to invest, or try to have our local industry players to expand their capabilities. So the tone is that we need the students to be an IC design ready prior for graduation. So there will be an increase for sure after the increase of human resource or manpower. Then that will try to transcend into increase in the economic growth in terms of these semiconductors and electronics industries. So, and the most important part there is to really establish or try to ramp up several startup companies that will try to invest or try to have this local IC design houses. So that will try to have a sustainable IC design ecosystem, starting from the human resource requirement from the output from the academe or the university. So the PIC initiative was there should be support on the faculty training. So it will start on trying to have faculty to be trained in IC design, initial steps, and eventually that will progress, that this faculty will be try to enroll themselves into the master's program in IC design, not only in master's but in PhD, either locally or train or have a degree abroad. So, and other option is to have this faculty immersion and the use of these particular EDA tools, and also summer immersion if ever the faculty cannot really be tapped during the regular semester. So the ultimate goal is to produce critical mass of IC design ready for the undergraduate level, and with the help of this particular initial train of faculty. So it was quite successful. The PIC expanded their trainings in the northern part of the country, but there's something challenging part in the middle of the country and to the southern part. So if you try to see the map, only San Carlos University, or University of San Carlos in Cebu and IMISO-IIT joined the force and try to promote all of this initiative. And if you've seen here in the right side of the slides, so Allen Luwaton and yours truly try to have these trainings of this faculty and student in other university. Me myself, I went up to the north, up to Baguio, okay, just to really help this initiative. But there's a little bit challenging, or there's several challenges that we encountered, because the sustainability is somehow need to be addressed. So therefore, the initial approach of giving trainings to the faculty and all the students doesn't really get somehow a big number in terms of how many faculty try to sustain and adapt the curriculum being given to them. So that is why we need to increase the level of stages. So the microelectronics program development have 3 stages. Okay. The first stage is this one. This is the stage 1, wherein PIC involved or try to give much role in it. So let's say they try to set the target that there should be around at least 2 faculty that will be trained out of the short courses, and with the help of the ADA tools, and try to have this particular laboratory affiliates or try to establish their own laboratory in the respective university. So again, this is not really sustaining. So that is why the best part is try to level it up to a stage 2, and faculty should have an MS degree or PhD degree in terms of IC design, so that they will really feel and try to relate the knowledge to the students effectively. And that is now trying to increase the level of let's say confidence of this particular faculty to engage also not only in the instruction or trying to share the knowledge what is there in the book or the textbook, but really put the design into an actual chip. So that is why we need to try to promote this time that the faculty will be having not only training or short courses, but to have the degree itself. So there are already success story to this. One of the example is the graduates of MSUIT MS degree. They are now somehow join other universities as like USTP, Caraga State, or the Surigao State College and Technology, wherein we could really assure that this faculty could have somehow a good glimpse, or let's say have the high capability to share and try also to have the R&D activities be done in the universities. So we are supporting in that particular sense, but we are not also discounting some short courses, because that is the only way to promote and try to allow faculty to somehow increase their level of awareness, at the same time to be loved with this particular microelectronics. So the third stage is to establish the center. So this now we're looking forward that not only a simple lab, but it is a recognized center. It's like the Philippine Institute of Integrated Circuits, and we need to really need to have this one be funded by the government and sustain it further with the help of the industry partners. So we are still on the stage 2 and 3, and in that particular sense, if ever we could reach this far until stage 3, and somehow we could really tell that we will see these targets set on 2025 will be met, okay, in 4 years to come. So just to give you a glimpse on what happened on the PIC ecosystem. So this is what we call as the Philippine IC design ecosystem. So there should be a joint force with the government and to fund the initiative from the university, at the same time collaborated with the industry partner. So what you've seen there on the upper left side, so ADMATEL and the APDC, these are the DOST agency that will try to help the students, faculty, and the local and foreign semiconductors and electronic industries here in the Philippines to have some support in terms of testing, in terms of also prototyping, right? So that is the job of ADMATEL and APDC. And some support also from the government to fund the faculty to be trained abroad, just like we have one Professor Allen Luwaton who tried to have some more trainings in terms of mixed signal and He was funded by the Board of Investment, BOI, and it's collaborated with DTI and also with the help of the DOST. So what you've seen here on the left side, okay, these are the academic partners. So there are only few, but we really want to have more so that we will see a big critical numbers that will try to help the demand coming from the industry. So now for sure we should see industry partners support on this initiative, right? So there will be a useless effort if ever the graduates will not be absorbed by the industry players or the industry that are doing IC design. And one big companies is the analog analog devices. So you've heard previously in the previous speakers last week and the two speakers ahead of me. So these are company partners of 𝐒𝐄𝐈𝐂𝐒, and analog devices is one of the biggest player here in the country, and they are now doing IC design. So we are support to that, and for sure they are really needing more graduates who are into this IC design. And also lattice semiconductors are doing also in terms of digital verification and the RTL, and also they have their own FPGA. So that is why Lattice is also a good partner of 𝐒𝐄𝐈𝐂𝐂, together with SINEX Semiconductor or SINEX Design. SINEX Design, which already have their satellite office here in Cagayan de Oro, and I will present that one in the next slides. And we have a new partner called the Embedded Silicon. So this emerging company, and they are quite growing this time. And also with the new players that we need to engage in the next year or in the coming months. This is Silicon Verified or Silver. And also we have EDA tool partners like Cadence and Synopsys to have all of this particular activity be realized, okay, in terms of IC design. Okay. So what are those industry initiatives? So you heard about CP. CP stands for Semiconductor and Electronics Industries in the Philippines Foundation. So CP joined the force and tried to recognize that there's really a need for the Philippines to try to ramp up the activity in terms of doing IC design. So what you've seen here on the left side, there's what we call as market opportunities. That, for example, the very basic example here is the IoT technology. So it could shift the electronic manufacturing services to really put somehow a small chunk of a portion of their activity to do IC design. So that is the only way to give the Philippines a simple niche or a single niche or key products and technologies that the electronic manufacturing industry should focus from this year up to the 10th year, and the tone is 5 to 10 years. So this will try to develop a robust supply chain. So that is why CP promote or establish this initiative called PATS, and this PATS stands for Product and Technology Holistic Strategy. So this particular strategy or initiative that established by CP is not yet fully materialized, but they are really hoping that will be soon. Okay, because what you've seen here, they try to see that IC design could be a good or a potential sector that will try to cover up all of these major activities in terms of the big data storage, 3D printer, smartwatch, IoT devices, and the 5G wireless system, and these are all R&D activities. So this is somehow a good niche for the Philippines, and to put the Philippines to be the global to be one of the players in the global market in terms of IC design. So what are the detailed initiative of PATS? So there are they set the conditions that, of course, there should be government subsidies to develop local SMEs, and for sure we have also they also need to have the sectoral planning and to give some acceleration on the following. Okay, so first is for sure there's already initiative to produce a high-speed internet, and we are now moving forward to 5G, and sooner or later 6G will come try to give an evolution of the 5G. So somehow this internet speed should be well established first, okay? And an initiative of giving incentives to the companies and technology startups. And you've seen here on on the fifth item that they try to recognize the lab scale wafer fab and the IC design centers. So we are happy seeing this, that the industry through CP are recognizing that IC design would be the best possible niche for the Philippines in terms of the semiconductor and electronics industry. So what is this lab scale wafer fab? Okay. So it will try to somehow scale up, okay, the activities, not only doing some IC design, but also have our very own small scale wafer fab, even in a small scale up to the 3rd or 4th lithography. So to do not really on CMOS technology for the meantime, but at least we have this application of MEMS, publication of LED on the light, okay, on that particular sense, because it is too expensive to establish a CMOS foundry, especially it needs a clean water, it needs a stable power, and on top of that it is very costly, and the question of sustainability. So the first thing that need to be addressed is there should be several startup companies that will do IC design, and a huge manpower who are capable of doing IC design also here in the country. So second to that is for sure try to establish the IC design centers. So not only one centers, but the university could establish their own center and to produce more graduates, not only in the undergrad but on the graduate level. So that is now a support coming from the industry. And what are the challenges? So even if it is already established that there will be support coming from the industry, and the government should somehow support also to this call. So because government are really love seeing this particular tag that the product will be made in the Philippines, or the chip is made in the Philippines, right? So industry, academia, and the government should collaborate into one, okay, to establish this particular initiative. So the biggest challenge here is that we need to increase more manpower, not only hundreds but thousands of IC designers in the country, and not only in the undergraduate level, but also on the graduate, MS, and PhD. So there is already a recognition, the majority industry challenge, that there is a lack of talents here on the red box on your right side figure. So the local challenge is this manpower, not only in the undergraduate, but to elevate further the R&D. The faculty, the students should have the MS and PhD degree to try somehow in the next 3 years or 5 years that there will be several R&D or development here in terms of IC design, especially in the IoT technology. So I would like to walk you through on the UP Diliman Micro Lab chip design milestone. So They've done in 1990, they've done the 20 micrometer CMOS, and they acquired Cadence tool. So these are their initial initiative before, way back 1990. So they try to increase the complexity level. Up to date, they are doing on 65 nano, but moving forward to the 28 nanometer FDSOI technology. So these are the things that they have done so far. And we are collaborating with UP Diliman this time to really address this call to produce critical mass, not only in terms of in the undergrad, but on the MS and PhD. So I put this slide back because I want to emphasize that the trend was 2001 up to date. Okay, so there is already somehow a huge gap this time. Okay, it's more than, I guess, more than 4 years that there is no project funded with respect to this in terms of the these are all the activity in terms of manpower development. So it was stopped 2015, and we need to engage further. Okay, not only doing the R&D but also try to maintain the manpower development. Okay, because it's very critical. Okay, so for MSU IIT alone, okay, so this is the response of MSU IIT with the collaboration of UP Diliman since 2010 on the IC program. So we've done that one for 2 years, and we try to increase our capability from doing the analog and mixed signal, but we need also to try to engage in the SoC or system on chip. So that is why the birth of the micro IC in 2017. Sorry for the date, it's 2017. So this is now trying to have a more, let's say, capability of doing a system on chip, and sooner the RF design can be integrated, because of the moment the capability is only up to the digital mixed signal and analog combined into an SoC. So that is the video you've seen a while ago on the promotion of the micro IC. Okay. So allow me to give some recognition on the contribution of Microlab to MSU IIT. So it plays a big role establishing the Microlab solely in the year 2010. It is somehow you could tell that at that particular time there's only one elective being introduced or being offered to the ECE curriculum. So we try to concentrate because there's a huge demand from the industry and there's a big call from the government. So in that way, it paid off because with that particular concentration, MSU IIT, even if there is no PhD yet at that particular time, so we try. We are recognized as the one of the center of excellence in the entire Mindanao and Visayas region. Okay, there are only 5, as I remember, of BSECE recognized by CHED as a center of excellence way back 2015. And with that, the UST recognized also that it is a virtual center of microelectronics IC design in Mindanao. So with that said, there are several trainings because IIT cannot do it alone. There should be several universities who will help us to bring all this call into a critical mass of graduates in terms of IC design. So that is why we try to replicate PIC, because if you've seen a while ago, PIC cannot really logistical issues that it cannot really penetrate Mindanao because it will be costly and logistical issues somehow. So UP tried to tap MSU IIT that IIT could lead Mindanao for the proliferation and try to expand to invite more universities to join the force, so that we could really attract industry partners, not only establish or expand there in Metro Manila, but bring the company here in Mindanao region. So with that said, okay, we try to engage several industries. We are keep talking to the industry partners, analog devices, selling the human resource and capabilities, and try to have some collaboration in terms of research from analog devices, SiNex design, lattice semiconductor, and CAMP. So to mention, let's say, for example, for analog design, we tap them to have some engagement of the chip testing, and in SiNex design to have consultancy in the design or the front-end stage of the R&D development, and lattice semiconductor in the sense of giving some support in terms of the graduate level, sending them in doing their thesis in the company itself. And of course, the camp was there also very helpful for the EDA tools, and we are going to engage sooner officially the Embedded Silicon as one of our partners. This Embedded Silicon are the CEO. The CEO is a former president of SiNex Design. So we are now on the promotion on the latest project of my MSU-IIT called Micro IC. And I guess you heard all of this thing or read some articles or news presses in terms of this Micro IC. And we are really challenged for this because with that particular achievement, okay, that would be a strong proof that there's already capability for MSU-IIT, not only doing the curriculum development and try to sell to the university student, but also doing a product development or try to introduce more methodologies or develop more materials. So in terms of producing manuals. So that is why we are so glad that we try to attract one close university partner, industry partner, and this is SiNex Design. And SiNex Design officially established their office in Cagayan de Oro, located in SM downtown. Okay, it was launched in May 2021, but prior to that, because of the pandemic, they was not able to speed up their establishment in Cagayan de Oro. So the initial office was located in Iligan City for a few months before moving to Cagayan de Oro. So this is a big challenge for MSU-IIT to expand this particular industry partner. To tell you honestly, the industry partner SiNex Design are really wanted to expand the human resource, or let's say the number of engineers who will be working with them, especially in Cagayan de Oro, trying to engage further MSU-IIT so that there will be a commitment to produce more, not only in the BS-ECE, but also for the Bachelor of Engineering Technology, especially in the layout services. So the projection is to hire at least 300 or 400 on the target on the next 3 to 5 years. So that is a huge number, and IIT cannot do that. So USTP should come to USTP, Caraga State, and the nearby university, who will going to help IIT to produce these numbers of IC designers to join this particular industry partner. So not only SiNex Design, but also analog devices, lattice semiconductor, embedded silicon. So allow me to walk you through the humble beginning of the microlab. So it started just like a very simple laboratory, and because of the funding coming from the UST, so it evolved into a much better lab. Okay. You've seen here since 2000, the picture on the left, I graduated 2002, but when I joined as a faculty in MSU-IIT, sad to say, I still able to witness this kind of love. And that is why there's really an eagerness that there should be somehow a change of clothes, okay, or some, let's say, in a big improvement on the facility. So that is why you've seen here a much improved micro lab for the undergraduate, and we try to separate the graduate level and the funded project to have a more concentrated and isolation for them to concentrate their task. Okay, and there's what we call as meeting room for a more conducive discussion and brainstorming of the IC design R&D research. So what is the way forward? Okay, so the way forward is that there's a big demand in terms of the Internet of Things, or IoT, right? So there's a big market for that. Let's say, for example, there is around 600 billion. Okay, you've seen here in figure on the figure on the left. Okay, so that is the IC market forecast that continue to grow on the next 2 years. Okay, it's around 600 billion US dollar. Okay, and there should be a need for proliferation of electronics, okay, especially in terms of developing IC design of the Internet of Things, or IoT devices. So it is expected that globally there will be 1 trillion of IoT devices that will be deployed globally. But somehow this projection cannot be seen for now because there's a big challenge on the power management, deploying the devices with the use of battery and the like. So there is a huge R&D rooms, or there's a space that very high to dig in, okay, to do more on this particular area. So not only on the doing the, let's say, discussion or try to have some module development the undergraduate level, but for sure in the next 2 to 3 years R&D in terms of establishing the MS and PhD program to the different university could ramp up for the R&D in terms of IC design to address this challenge. So for example, let me walk you through on the UC Berkeley, UC LA, for them to produce research universities in terms of IC design. There should be a graduate, not only 100 but thousands of microelectronics and semiconductors engineers with master's and doctorate degree. So on the first bullet, so we are not seeing yet. We are too far from this. Okay, so that is why second to that is there should be a development and promotion of experimental technology, which is very vital for research university. And third to that is for sure that is more high level to translate the experimental technologies into a commercial product. So that can only be done if a faculty will be doing some sabbatical leave or try to engage or establish its own local company or local startup company doing IC design and hired the students to take part of that development. So time check, I have still 10 minutes. Okay, sorry for that. Okay, so let me introduce you on the IC design technology timeline, the scope versus the risk. So there is what we call as a system on chip or a system in package, and that would be a development of putting everything into a single solution. Okay, for example, the energy harvesting, the machine learning or the AI will be there on the IC itself with the RF and the data converters, the DAC ADC, and the analog part. Okay, and also with regards to the automation, so there will be digital control or digital MCU, GPU and MCU to that. There should be somehow some development stage. Let's say, for example, you've seen here on the right side that the academe or the university has the huge time to do some preliminary research or R&D. Okay? So that would be at 10 years ahead. Okay? So let's say you will have here a more technological technical scope, okay, for the academic to do exploration research. Okay, so that will try to decrease the time as it will going to progress to strategic research, technological development, and manufacturing. So the role of the academic or the role of the university, okay, is to train these IC designers to be ready to join the industry, and because there is a really a huge cost for a failure. So the manpower should be well trained and equipped to do IC design. So it's not just like a short course or a very let's say less than 1 year training. So there should be a degree for the university to offer in terms of graduate level for the faculty and the students to be trained with this particular IC design need. So with that said, if you try to check the roadmap, okay, let's say for example for IoT, I have closed this one in box, in the red box. So let's say for example in the year 2034, so for IoT there will be few devices in terms of CPU that will be put in place. So for example in this year 2022, in the coming year, so the projection is they will have around 2 CPU, but for the next decade there will be triple number of CPU for the deployment of IoT device. And previously for the micro IC, we only have one CPU to that, okay? And there will be a lot of improvements later on for the IoT development. But what is being steady here in terms of the power requirement is that the energy source would be somehow a mixed source, either battery or the energy harvesting. So that's why B plus H. So still we've not seen a trend or a roadmap that someday somehow these IoT devices will have a very, very low or ultra low power, wherein it could be powered alone by the energy harvesting or the ambient sources without battery. So with that projection, that was projection by the IEEE IRDS, okay, in the year 2020. But locally, there is what we call as a roadmap set by DOST and BOI. And that roadmap, you've seen here that in last year or this year, okay, so we've done already this particular green text 2021. It is done already in green text color. So the PMU, HU, and MCU, so that is a project of the micro IC. So that is why DOST and BOI put that one in this year 2021. And in the next 3 years, 2024, okay, we will going to see that there will be what we call as establishment of wafer fab and IC design laboratory. So that's the one that's set by CP. Okay, and we are also hoping that with the initiative that we are doing currently with UP Diliman and MSUIT, we propose something that to elevate further, okay, the engagement, not only the manpower development, but in terms of R&D to develop a new technology. So not the regular CMOS, but the FDSOI technology. So there's still a lot of things to do in terms of the IC design. So that is why, okay, with the help of CP, UP Diliman and MSUIT join force and collab and try to project and create this roadmap initiative that I cannot yet disclose the details on this. That is why I erase some text on the right side, because it is not yet fully approved. It is still on the process of approving under the DOST, but I could share to you that someday in the next few months, okay, if ever it will be fully approved by the UST, that a new let's say a possible center, okay, that will be funded by the UST with the help of CP, okay, that the initiative of manpower development and R&D will be combined together, just like what you've seen here on the upper arrow. So these are the fundamental research complementary, okay, and this one is the lower arrow is the manpower development, and this should be combined together to create an applied research plus what we call as manpower development, and that will be somehow in turn we've seen in the next 5 to 10 years that there will be center, okay, national center that will help the industry and address the call that the Philippines will be seen, okay, as one of the frontier in doing IC design. So we will take advantage to that. So I'm going to call students, okay, hopefully that if you are not into IC design yet, so I really going to promote at this very early stage that if ever we will going to engage this IC design activities right this year, so there will be let's say 5 years, okay, so the enclosed box in the next 5 years, 2025, okay, we will be trained this time, and you will be more sellable up to 3 to 4 years, especially doing the applied research to the industry, because it will take so much time for you to be fully equipped in doing R&D. So in that particular sense, you will be more attractive by the industry, and that will be let's say you could now produce more research, okay, more R&D research in doing IC design. So the IC design in education, if you'd like to see here in the figure, that we are on top of the food chain, okay, seeing that one on the top of the food chain, okay. So because IC designer is a problem solver, it's an enabler, an explorer, so we need to combine the skilled manpower and the academic research. So we are not really promoting that you could produce chip to sell to the industry, or having your own chip to sell to maybe not only to the industry partner, but to sell to the foreign companies. But what is very sellable here is that the methodology, because the chip that we are taping out is just an embodiment or artifacts, but the high value is that the methodology that you carried in when you try to join the industry or try to build your own local startup. So in that sense, okay, have you seen here on the right side some evolutions, okay? Doing IC design could really try to enable, okay, this particular product, okay, either in the mobile system or the portable devices, and of course in doing some smart cars, okay? So how to leverage the technology? So if you try to check, if you are an IC design, so start with the analog background, okay? So that will be the fundamental technology, but the primary linchpin of all this applied research is the RF. So that will try to have some similar products. Let's like the space or aerospace IC in that particular application, and the Internet of Things or IoT, and the automotive radar navigation. So we are now seeing a trend that CMOS will be evolved and evolved into a much low power devices. That's why there is already a FENFET and FDSOI technology to resolve all of these challenges of this particular application, because they requires a very, very low power. The aerospace, Internet of Things, and the automotive radar navigation. So the most effective technology roadmap is that there should be IC design perspective plus, okay, an awareness of the roadmap, so that it will be much efficient for the use of the resources, just like time, manpower, and money. So hopefully we are going to see that the Philippines will be the next frontier of the semiconductor and electronics industry. So we need to increase this availability of talent in terms of IC design, and we are calling you who join here in this webinar, especially those graduating students, to don't stop the undergraduate. There is so much more to learn. Okay? And for you to be an IC designer, you should have an MS degree. That is a very primary requirement. Okay? You can also do IC design, but you will be on the services and doing the layout services, something like that, if you will going to stick only on the undergraduate level. So that is why I'm calling you who are here or still in the undergraduate. If you are graduating and the junior students, kindly consider come and join us, learn IC design while earning. And why earning? Because there is a huge fund coming from the UST. This is what we call as the UST Early Scholar. I guess 25,000 is pretty much attractive for you to learn at the same time earn, right? And join us to address this call and before you're going to join the industry. And for sure, you are very much attracted then if you have this skill set. And I guess that's all for my talk. Thank you so much. I'm just on time. Thank you, Rochelle. Any question? I'm glad to answer all of those questions.
All right. So thank you so much, Sir Jeff, for that very comprehensive talk, no, an inspiring talk for us to really pursue microelectronics, especially for those universities who haven't yet offering the microelectronics field, no, in their respective departments. So we will now go ahead and take some time for some questions now. So we have here a question from Sir Darwin Maniaga. So he said, interesting presentation. I understand the importance of increasing the number of competent IC designers. Just curious if there is also a drive to leverage the development of competent test development engineers. Is there a test lab in MSU?
Okay, thank you, Darwin. That's a very good question. Thank you for raising that one. Yeah, there should be a leverage because for sure you will be a good test development engineer if you could also do IC design. So in that particular sense, for example, the question is there a test lab, okay, in MSU IIT? So initially we cannot really test the chip thoroughly. What the industry are doing, same as what the industry are doing. We need the help of the industry partner. That is why I mentioned this on the previous presentation. There's one slide there that I mentioned that in the project that we have in the Enlight project and Micro IC, we tap EDI, analog devices, to help us make use of their test equipment, the high grade test equipment, for us to evaluate really thoroughly the chip itself that we fabricated. And that is somehow, there's somehow a time constraint to do all of those things. So for the meantime, MSU IIT don't have yet the full capability of doing the test alone. So we have small lab there for testing, but some test equipment is not yet procured for high-end test equipment. So, but functional test is there already, right? Just like a simple oscilloscope, okay? And also some high-grade power supply and so on. But we are really looking forward that even we are trying to have our own wafer proving station so that we could really characterize the wafer itself outside the package. So that is somehow we are looking forward. But we are so happy that with the industry partners that we have, they are willing to help us to do all of these things. Rochelle, thank you.
Okay, sir. Thank you so much for that answer. Another question from Sir Darwin is just curious, any idea on what happened to PIIC? It sounds like they discontinued operation.
Yeah, okay, yeah. What happened to PIC? Even if there is a goal, the initial goal of PIC is to transcend into just like what Taiwan has, right? Or Taiwan E3 or the CIC of Taiwan. So it means that it will going to support the university partners to have their own EDA tools. So the PIC should act as a center, not only providing EDA tools to the university who will be doing IC design, but at the same time, be the center to cater all the tape outs coming from the students' researches, especially for those who are doing MS. But unfortunately, it was discontinued and not funded by DOST further, in the sense that they are seeing that PIC should have some sustainability plan, that they will not going to depend further from DOST funds. They will act as like an independent, independent entity that it could be standalone, either industry or some other investor to come in outside the funds of the DOST. That is why the birth of the camp, the Center of Applied Microelectronics and what is camp? Yeah, programming. Center of Applied Microelectronics and Programming. So that is now the second version of PEIC, or the next version of PEIC. So, but it is now a private company, and the CEO of the camp is the former program lead or project lead of the PEIC. So that is why we are proposing something now, with the help of UPD1 people, that it is somehow a good version or higher version of PEIC. And I will disclose that one once it is approved, and I will share to you in the next 2 to 3 months, once it will be fully funded by the OST. And help us to pray for that. Thank you, Rochelle.
Okay, sir. So there are a lot of positive remarks about your topic given this afternoon. We have a bright future for IC industry, and thank you. I think everything is very well explained through your discussion, Sir Jeff. So, any more questions from the audience? Okay. Okay, they are all grateful for your sharing of your ideas and thoughts about the microelectronics here in the Philippines, sir. So, if there will be no more questions, we will be proceeding with the award of Certificate of Appreciation to Sir Jeff. Okay, this Certificate of Appreciation is given to Engineer Jefferson A. Hora for having shared his knowledge and expertise on microelectronics journey in Philippine education during lecture series on microelectronics session 2 held at Zoom web conferencing on October 30, 2021, accreditation number ECE 2009-001223, signed by the Governor of IECEP, Iligan Bay Chapter, Olga Joy Herasta, and Secretary Genevieve Gatar. Okay, so all right. So now so we will proceed with the evaluation, and online quiz once again. Thank you so much, Sir Jeff. And by the way, while you are answering the online quiz and evaluation, we'll also be having the closing remarks of our ISAP Iligan Bay Chapter Vice Governor Internal, Engineer Ailen Gomera. Good evening, everyone. First and foremost, I would like to express my appreciation to the speakers and panelists for their valuable contribution to our IECEP IBC webinar. Thank you for imparting your knowledge and wisdom in the field of microelectronics. On behalf of IECEP IBC, I would like to thank everyone for attending this microelectronics webinar and help to make it such a successful event. Thank you all and have a good evening. See you in the next webinar. We will keep posted in our FB account, IECEP IBC Iligan Bay chapter for the next webinar. Thank you. Okay, so can I hear? Okay, by the way, for those participants who would like to have a copy of the recorded video and also the presentation of our dear presenters, you may send your email at isep.iliganbaychapter@gmail.com. So to make it more organized for us to really consolidate all those materials and then send to you via email. So first, send your email to this IECEP Iligan Bay chapter email. Then we will forward to you the resources that you are asking for. Okay. Okay.